Okay. Good evening. Good evening. Can you hear me? Thank you, Harsha. Yeah, good evening. Good evening. Good evening, Vamshi. Good evening, Sandeep. Good evening. Good evening, everyone. Right? Let's get started. Yesterday, we have seen few of the band gap references, right? Where VB1 minus VB2 is nothing but VT log IC1 by IC2. Am I right? See, one of the popular band gap reference, this is also a gate problem. So this is also a popular band gap reference. The examiner wants you to find VB1 minus VB2. This is VB1, this is VB2. And VB1 minus VB2 is nothing but Vx. So we all know by virtual ground, the voltage at non-inverting will be voltage at inverting. So a similar circuit is given by the gate examiner. He said find Vx. Transistors are non-linear. Non-linear with IC equal to IS into e power VB by VT. So they obey a relation IS into e power VB by VT and VT being 25 millivolt. 25 millivolt. Find Vx. So a similar problem is given in gate exam, right? So how do you find Vx? Now, whenever there is negative feedback, the voltage at non-inverting, what is the voltage at non-inverting here? The voltage at this point with respect to ground is VB1. So this node is also at VB1. So this voltage is also VB1. Am I right? Voltage at non-inverting is equal to voltage at inverting. V plus equal to V minus equal to VB1. Now what is Vx? Vx is going to be VB1 minus VB2. Vx is VB1 minus VB2. So what is VB1 minus VB2? It is VT log IC1 by IC2. VB1 minus VB2 equal to VT log IC1 by IC2. Am I right? Suppose if the examiner says transistors are not nonlinear, they give you a drop of VD on equal to 0.7. Then what is VB1 0.7? VB2 is also 0.7. 0.7 minus 0.7 is going to be 0. 0.7 minus 0.7 is going to be 0. But here the transistors are nonlinear. So there is a slight band gap between VB1 and VB2. The examiner wants you to calculate that. But VT is 25 millivolt. What is IC1 and IC2? What is IC1 and IC2? In the question, he has also given beta large. So what is IC1 and IC2? IC1 is a current through 1K. This is IC1. And this is IC2. And this node we don't know, we'll call it V0. V0 here. So tell me, what is IC1? IC1 equal to V0 minus VB1 by 1K. Am I right? What is IC2? IC2 is V0 minus VB1 by 10K. V0 minus VB1 by 10K. So what is IC1 by IC2? V0 minus VB1 gets cancelled. It is 10K by 1K, which is 10. So IC1 by IC2 equal to 10. Therefore, VT is 25 millivolt, log IC1 by IC2 is 10. So this is the answer, right? VB1 minus VB2 equal to VT log IC1 by IC2. IC1 is nothing but current flowing through Q1 transistor, right? IE or IC both are same. IB is neglected. IB is neglected. So this IC or IE both are same. So what is IE or IC? V0 minus VB1 by 1K. IC2 is the same, V0 minus VB1 by 10K. So IC1 by IC2 is 10. It is 25 log 10. 25 log 10. How much is 25 log 10? 25 log 10. Akash is telling me 57. Rohit 57. Himanshu 57.56. Very good. 57.56 millivolt. So this is your Vx. So VB1 minus VB2 is VT log IC1 by IC2. Your Vx is around 57.56 millivolt. Right? Now, yesterday we have seen the level shifter circuit, but generally in exam, the level shifter output is given as 0. But with 0 volts, that is not a proper design of a level shifter, because level shifter is in the third stage of op-amp. After level shifter, we will have a power amplifier. So the power amplifier also needs a voltage of 0.7, is it not? So level shifter output, if it is 0.7, it is better, because the next stage it has to again give. So it's almost like what should I say? If you have a piece of bread, you have to distribute. By the time you reach the output of an op amp, you should not be left with any DC offset. It should be zero, because we don't have capacitors inside an op amp, right? So the moment you connect a supply to op amp, plus 12, minus 12, all the transistors inside the op amp should be on with plus 12 and minus 12. But they should take 0.7, 0.7, 0.7, 0.7 every transistor. By the time you reach the last node, the output node, you should be left with 0 volts. Then you don't need any capacitor. You don't need any capacitor. So say for example, I am having a circuit, a simple amplifier. This is something which I have drawn in my introduction, is it not? Just for fun I have drawn, but it is not for fun. It is a serious circuit only. Because for this circuit, you can do DC analysis and AC analysis now, because we have become a little matured enough now. So just by inspection, we are not going to do any big analysis. Just by inspection, you have to tell me, suppose these two are the non-inverting and inverting terminals of op amp. I am grounding it. How will you design an op amp? When both terminals are grounded, the output should be giving you a DC offset of 0. When you connect a supply of some voltage, say plus 12 and minus 12. So let me connect here plus 12 and this is minus 12. Then how will you design the level shifter circuit? This is the second stage, Darlington pair. The third stage is level shifter. For this level shifter, you can use the same current mirror. And the last stage is some power stage, power amplifier. Now tell me, how will you design the value of resistance R? Suppose if I say find R such that when V in is 0, V plus equal to V minus equal to 0 volts, your V naught should also be 0 volts. V naught should be 0. V plus equal to V minus equal to 0 and your V naught. So how will you design a level shifter? Say for, I'll give you some values here. Yeah, now you can start. Tell me, if this is plus 12, this is minus 12, how much voltage is here? Let me change the color of my pen. How much voltage is here? 0.7, right? So this is minus 12 plus 0.7, it is minus 11.3. Minus 11.3. So here you have 12 volt. 12 minus of minus 11.3 by 23.3K. For simplicity, this is 1 milliampere. Now here I'll have 2 arrows. That means 2 transistors are in parallel. 2 arrows means 2 transistors in parallel. 3 arrows, 3 transistors in parallel. 5 arrows, 5 transistors in parallel. So there are 2 transistors in parallel. So you'll have 2 milliamp. If this is 2, this is going to be 1. This is also going to be 1. Now tell me, what is 12 minus 4? 8 volt. So still bread is there, 8 volt. From 12 volt headroom, 12 volt to minus 12 volt, 24 volt headroom, you have 8 volt in the middle. Now, by the time you reach the output, if it becomes 0, then you don't need any capacitor, is it not? Now tell me, this is a diode here, this is also a diode. So a Darlington pair takes a 1.4 volt. What is 8 minus 1.4? This is going to be, this is 1.4 volt. It is going to be 6.6. 6.6. Now what is 6.6 minus 0.7? 6.6 minus 0.7, it is 5.9. 5.9. Now let us come in the reverse process. Let us come in the reverse. This V naught should be 0. This V naught should be 0. I lift this up. This should be 0.7. No? If this V naught is 0, this is 0.7. That means the resistor should drop a voltage of 5.9 minus 0.7, 5.2 volt. 5.2 volt. but the mirror current here is 1 milliamp. The same mirror I'm using, 1 milliampere. Now this is simple Ohm's law. What should be the value of R so that your output is 0? So this resistor should somehow drop 5.2 volt. Now you tell me 1 milliamp current is there, 5.2 volt. That means that resistor, what is the solution for this whole problem? R equal to V by I. That's a Ohm's law. Everything is Ohm's law. 5.2 by 1 milli, 5.2K. Now, if you put 5.2K, then we'll come again from the beginning, we will come, right? First, there is 1 milli here, right? 12 minus of minus 11.3 by 23.3, 1 milli. Then this current here is going to be 2 milli. It is split into two parts, 1 milli, 1 milli. Then here there is 8 volt. 8 minus 1.4, 6.6. 6.6 minus 0.7. 6.6 minus 0.7, 5.9. But here the resistor is already 5.2K. 1 milliampere is flowing 5.2K. 5.9 minus 5.2K, 5.2 is going to be 0.7. 0.7 minus 0.7. Tell me what is 0.7 minus 0.7? 0. Now, is there any need for you to have a what you call capacitor? No need, not needed, is it not? So we have calculated in such a fashion that finally that extra 5.2 volt you need to drop that 5.2 volt with 5.2K because the current is mirror current, right? 1 milliampere. So we were able to, so with no input, this is a non-inverting terminal of op-amp. This is the inverting terminal of op-amp. When you ground both the terminals, your IC says that there is no DC offset of 0. Now, you give a signal now. Now you give a signal, give feedback, 1 plus RF by R1, non-inverting amplifier gain, minus RF by R1, inverting amplifier gain will come, but DC offset will be 0. Suppose instead of 5.2, if it is 4.2, what will happen if it is 4.2? 5.9 minus 4.2. That means there will be 1.7. Output is going to be 1 volt, no? So any signal that you give, it will have a DC offset of 1 volt over which amplification will be there. Now a customer will pull his hand. He will think why this 1 volt has come. This 1 volt has come because you didn't block that DC. So a proper design of level shifter is important. If you do a proper level, R equal to V by I, that's all. 5.2K if you put, then your output will always be 0. Am I right? Okay. Now as a homework, what I want you to do is, this is DC analysis. This is what analysis? DC analysis. I want you to take stage by stage and do AC analysis. AC analysis. How can you do AC analysis? Suppose last stage is there. Can you see the arrow here? Right? Can you see the arrow? What is the input resistance of a CC amplifier here? R pi plus 1 plus beta times of RE. That in parallel with R naught here. That in series with R. Then what is the input resistance here? It is again R pi plus 1 plus beta times. So like that, stage by stage, you can calculate input resistance. Input resistance here, input resistance. What is the input resistance here? R pi plus 1 plus beta times of RE. Can you see here? Yes or no? R pi plus 1 plus beta. Like that, stage by stage, you can do. This is only DC analysis we have done. AC analysis, you can very comfortably do stage by stage. Are you getting? So this is a simplified diagram of an op-amp. There's a simplified diagram of an op-amp, right? The first stage is a differential amplifier biased by a current mirror. The second stage is the gain stage, Darlington pair. The third stage is the level shifter. And the last stage is the power stage. So when no DC offset is given, when no input is given, the moment you give plus 12 and minus 12, biasing is done. And the whole biasing is because of this single diode here, right? The moment the diode is on, happily 0.7 volts it is giving, right? All the devices are on with negative supply. You don't need voltage divider bias anymore, right? Because of the positive and negative. Slowly what we can do, what they have upgraded, all these resistors also they have converted. Are you getting? All these 4K resistors are there now. They have converted into PNP current sources. PNP current. Then the gain will be very high with active load. You will not have minus GMRC. You're going to have minus GMR naught. You're going to have minus Gm into R naught. Are you getting? Okay. So level shifter, and in the present day world, there is no level shifter and all that, right? If the load is a capacitive load, the load itself will block DC, no? And the last stage is power amplifier, CC amplifier. Second stage is gain stage. So if you remove the middle stage, level shifter, if you remove, the second stage and fourth stage are similar, because second stage is also common collector. Last stage again common collector, not needed. So if you remove the third stage, level shifter, then op-amp can have two stages only. So the buzzword these days is two-stage op-amp. Four stages, 741. The old op-amp used to have four stages, minimum four stages, right? So wherever a transistor is there, resistors are there, you can connect a PNP current source. Then what is the R0 value? What is the resistance offered by a PNP transistor? It is going to be R0. It is going to be R0. So that we have already seen, isn't it? We have already seen a simple common emitter looks like this. Instead of putting a resistor here, you can put what device? A PNP current source. So wherever resistors are there, you can have an active. This is passive load. This is going to be active load. If you use an active load, then what is the gain? Here the gain is going to be minus Gm into Rc. But here the gain is going to be minus Gm into, this guy is R0, this guy is another R0, R01, R02. Or if both transistors are same, R0 by 2, R01, R02. So all the passive resistors, you can convert it into active so that you get more gain. Isn't it? Okay. Fine. So what shall we do today? Today, we are going to see simple Zener circuits. So in the differential amplifier, if you don't like two arrows, put two transistors here. Are you getting? Some students don't like two arrows. In spite of telling them 5-6 times also, they will say, why this current has come. Are you getting? So put two transistors, 1 milli here, 1 milli here. 1 milli plus 1 milli is 2 milli. Are you getting? Two transistors in parallel means 2 milliampere. Three transistors in parallel, 3 milli. So I have already given you a notation. If two transistors are in parallel, so much of ink will be wasted, no? Pen. So instead of three transistors means still more, like that you have to keep on writing, right? So then for some students hand will pain so much, right? So instead what they will do, they'll put three arrows like this. Three arrows means three transistors. Are you getting? It's just a simple way of drawing, right? Whenever I put two arrows, it means there are how many transistors in parallel? Two transistors in parallel. Okay. So let us have a simple Zener circuits today. So this week we are going to complete. By Sunday, we are going to complete. And next week you can have a new subject, right? See, any subject you take, only 4 bits will come. Are you getting? So even if I teach little here and there also, nobody will question me. Is it not? But that is not the criteria. The criteria here is not those 4 bits. A student has come here, he has to learn. That is more important. Yes or no? What is there? One question from BJT will be there. Or if DC analysis we give, AC analysis we will not give. 1 or 2 questions from MOSFET, right? And then out of 4 questions, 8 marks, 1 mark, 1 diode problem here and there you will give in a finished over. Analog part is over. So 1 op amp, 1 diode, 2 MOSFET, 1 transistor means finished. There is no scope to ask more. But that is not what for you have come here, is it not? 4 bits, 4 bits, any subject you take, only 4 bits will come. Some subjects 3 bits, 2 bits, is it not? It is not to attempt only those 2 bits we have come. So you have to learn, that is more important. Are you getting? Now, why do we need a Zener, right? Why we have introduced a Zener here? We have seen rectifiers, is it not? So suppose what is readily available to us, or this topic is light-heartedly called as how to get VCC supply. Because till today we thought every amplifier has VCC, but now we are thinking, what is readily available in our house is 230 volts RMS. We don't have VCC supply. Then how is that you are going to give VCC supply for all our BJT amplifiers? So you have 230 volts RMS. So you need a step down transformer. A step down transformer followed by rectifier or some rectifier, bridge rectifier like that, right? The rectifier output is given to a peak detector or low pass filter, right? Any capacitor in the shunt arm here, we can always call it as an LPF, low pass filter, peak detector. Peak detector output, we have to give it to voltage regulator. So here our Zener will be there, right? Zener, some error amplifier, pass transistor, some op amp circuit, BJT circuit will be there. And the output, you can connect it to the load. So what is load here? What is load? Load is not 3.3K, 4.7K load. Who is load here? Load is our amplifiers, right? This load is nothing but our amplifier, CA amplifier, CAB amplifier, CC. All our amplifiers are load now because they will have a VCC supplier. Load will have VCC. This VCC will use it for all our amplifiers, right? Because what is available to us is only a AC waveform. AC waveform. First, you need to step it down. But after stepping it down, we need a unidirectional rectification. You need rectification. Then after rectification, you need a capacitor which will quickly charge but slowly discharge, quickly charge, slowly discharge. So this capacitor output should be some kind of a ripple like this. But this ripple is unregulated. If you give this to a Zener, then the Zener is going to give you a constant voltage, 5 volt or 9 volt like that, right? So this 5 volt, you can use it as VCC supply. So first we have to step the signal down. After stepping it down, we need a rectification. And after rectification, that is unidirectional, right? Pulsating DC. You have to make it, you have to decrease, right? The ripple by connecting it to a peak detector. Still some amount of ripple amplitude is there, right? So that you can decrease by connecting a Zener circuit. So once you give it to a Zener, from this ripple, you will get a constant DC output, right? And this DC output, you can use it as a VCC supply for all our amplifiers, right? Okay. Or these days, even regulators, they are coming in IC form, right? So you can take a center tap also, 12012, something like that, a transformer. You can have rectifiers, diodes like this, and then a peak detector is a capacitor. So this circuit we have already seen. This you can give it to regulator 7805, and the output is going to be 5 volt, right? So this you can use it as a VCC supply, because when when op-amp was done, right? So people were using op-amps and everybody were happy using op-amp. There's nothing happening in analog, right? Op-amps, better op-amps, still better op-amps, like that. Then they felt that they want to simplify power supply design, because the power supply design looks complicated in the whole what you call voltage regulator circuit, or in the whole DC power supply. This is the DC power supply. This is how you make a DC power supply. And in the whole flow, right, the signal flow, the most complicated thing is the voltage regulator. So then they felt, why not simplify the regulator design, because there's so much of market there, right? So then they started building voltage regulators, right? And now we have ICs. So many different ICs are there. Popular ICs are the 78 series, the maximum 1 ampere current you can get. 7805, 7809, 79 series is also there. That will give you a negative supply, right? Okay, so we'll go slowly. First of all, initially, we are not going to do the IC here. What we are going to do is a crude form of a voltage regulator with a diode called a Zener diode. A diode called a Zener diode. What is the characteristics of the Zener? Characteristics. What is the characteristics of Zener? Now, I told you polarities will always come with the direction of current, right? So if the current can flow in this direction, current can flow in this direction. That's a good thing about Zener. But whenever current goes from anode to cathode, the polarities are like this. Zener is going to give you a small voltage. But whenever the current flows from cathode to anode, because polarities will always come with the direction of current, Zener is going to give you a large voltage Vz. So Zener is a diode that can work even in forward bias as well as reverse bias. But the only difference is it will give you a small voltage in forward bias and a big voltage in reverse bias. And Zener does not have polarity. Zener does not have polarities. Polarities will come only with the direction of flow of current. So what is the characteristics of Zener? The same, what you call, this is V and I. You can take V and I, and the characteristics looks like this. My hand is shivering. This Vz can be 5 volt, 6 volt, like that, right? Or you can have a ideal characteristics. An ideal Zener. Look like this. Okay, so the Zener here has got 3 segments here, segment 1, segment 2, and segment 3. So what is segment 1? Segment 1 says that the current flowing through the Zener is positive, and the voltage across the Zener here is going to be 0.7. So Zener can be replaced by 0.7 volts whenever the Zener sustains a positive current from anode to cathode, right? Now, what is the second segment? The second segment says that here in this segment, the current flowing through the Zener is zero. Current is zero. Current is zero. And the voltage across the Zener is going to be between anywhere between what? 0.7 and Vz. So it's Vz and 0.7. So it's anywhere between Vz and 0.7, right? So the Zener is replaced by open switch. So we'll come to this because in positive direction it is 0.7, in the negative direction it is Vz. So it all depends on the nature of current flow, right? So in the second segment, when the current is zero, the Zener is replaced by an open switch. Now what about the third segment? The third segment says that however current changes, the voltage across the Zener is Vz, right? So Zener can be replaced by a DC source. The Zener can be replaced by a DC source. So Zener has got three phases now, right? Three phases. It can behave, and be careful, the examiner, gate examiner, will somehow make Zener an open switch, and then he'll ask you to calculate the voltage. So that's terrible, right? So the Zener is not at all working if the voltage is between 0.7 and Vz. If the voltage is between 0.7 and Vz, the Zener doesn't work. If your voltage at the input is somehow greater than 0.7 volts, then the Zener will go forward bias. If it is anywhere less than Vz, it is going to get reverse bias, right? I mean, it's going to give you a constant voltage. Fine. But if it's anywhere between this voltage, then if the current is zero, then the Zener is replaced by open switch. So we'll talk about this. So our aim is not Zener, our aim is the voltage regulator. So if you have Zener in this fashion, and you have given a positive voltage, then tell me what is the polarity of Zener? Polarities of Zener. Current always flows from higher potential to lower potential. Current always flows from higher potential to lower potential. So when the current is flowing in this fashion, what is the polarities for Zener? What is the polarities for Zener? Polarities will always come with the direction of current, right? Plus minus, plus minus, plus minus, plus minus. These are the polarities. Now, what voltage should I take? Because I've given you two voltages here, 0.7 and Vz. So when will a Zener give 0.7 and when will a Zener give Vz? Whenever the Zener is forward bias from anode to cathode, it will give 0.7. If the Zener current flows from cathode to anode, it gives Vz. Cathode to anode, Vz. Anode to cathode, here it is going to give 0.7. Right? 0.7 for forward bias, Vz for reverse bias. Polarities will come with the direction of current. Suppose the same circuit, if I draw it in this fashion, and the polarities of the input is like this, then how will the current flow? Current always flows from plus to minus. So the current is going to flow in this direction. Right? Then what will be the polarities for Zener? So polarities will always come with the direction of current. So tail is plus, head is minus. So Zener does not have polarities. Polarities will come with the direction of current. But in this travel, when you go from down to up, if you go from anode to cathode, it is forward bias. Cathode to anode, it is reverse bias, right? Now you're going from cathode to anode. So it is Vz. Anode to cathode, 0.7. Cathode to anode, Vz. Anode to cathode, 0.7. Anode to cathode, 0.7. So is it difficult? Nothing, is it not? First take the current direction. See if it is a chota voltage or bada voltage. If Zener will give you a chota voltage if it is forward bias. Zener will give you a bada voltage if it is reverse bias. And the polarities will come only with the direction of flow of current, right? Okay, find V naught. Vz equal to 5 volt. Vd on equal to 0.7. For all these Zener problems, we will take 0.7 for forward bias and 5 volt for Zener reverse bias, unless and until I mention it, right? Otherwise, we can have these two numbers. This is a gate problem. Okay. Now, all of you, see here. I told you polarities will come only with the direction of flow of current. Am I right? The current always flows from plus to minus, plus to minus. So this is a Zener where you take the output, but the direction of current is like this. If current flows from anode to cathode, if the current flows from anode to cathode, what is the drop across the diode? The drop across the diode is 0.7 volts. The drop across the diode is 0.7 volts. Therefore, you can apply KVL around this loop. KVL minus 0.7 plus V naught equal to 0. Your V naught is 0.7 volts. Your V naught, so when the current flows from anode to cathode, there is a drop of how much? 0.7. It is going to be 0.7. That means the Zener is forward biased. Zener is forward biased. I told you if Zener is reverse biased, then it will give you a large voltage, VZ. If it is forward bias, it is going to give you a small voltage. Chota voltage in forward bias, bada voltage in reverse bias, right? Now, by the polarities of the input, this is the direction of current. Am I right? This is the direction of current. So you have a diode here, and I want the output V naught. And look at the direction of current. The direction of current is from cathode to anode, cathode to anode. Now, with 12 volts input, Can't you get a 5-volt drop? Is it not? The Zener is what bias? Reverse bias here. The polarities will come only with the direction of current, right? So this is a nice diode. You can take current in any direction. But if it flows from anode to cathode, small voltage. If it flows from cathode to anode, big voltage, right? So because the diode is reversed here, now the current is flowing from cathode to anode. So naturally it is giving 5 volts. So now you can apply KVL around the loop. What do you get? Minus to plus, minus 5 plus V naught is 0. Your V naught is going to be 5 volt. So your V naught is at 5 volt and the Zener is not forward, but it is reverse bias. It is reverse bias. And if a diode is for, otherwise, if it is a normal PN diode, what will happen if you have a normal PN diode? If it is a normal PN diode like this, and you give 12 volt, what will happen? This diode is reverse bias. When it is reverse bias, it will behave like an open switch. It will behave like an open switch. Then your output is going to be 12 volt, the same 12 volt. Am I right? But if it is a Zener, then the Zener will go to breakdown. The Zener will go to breakdown, and your output is now going to be big voltage, 5 volt in reverse bias, forward bias 0.7 volts, right? Now don't look at the Zener, look at the input, right? Look at the input. Whether if it is a sine wave, whether it is a positive cycle or negative cycle, like that, right? It's only a DC voltage. There's only one current flow from plus to minus, right? It's a static DC voltage. This is plus minus. So now this is the flow of current. Am I right? This is a flow of current. Then what is V naught? What is V naught? You have a diode like this and a diode like this, right? And the current is flowing in this direction, So tell me, plus minus, plus minus. What voltage should I give for upper diode and what voltage should I give for lower diode, right? The upper one is forward bias, so I have to take 0.7 volts. And the lower one is what bias? The lower one is reverse bias, right? So the anode to, this is anode to cathode, this is cathode to anode. So anode to cathode 0.7, cathode to anode VZ. Then what is V naught? V naught is going to be 0.7 plus VZ. It is 0.7 plus 5. It is going to be 5.7. It is going to be how much? 5.7. The diode is going to give you 5.7 volts, right? The upper diode is forward bias and the lower diode is reverse bias. So Zener is a diode that will conduct both in forward bias as well as reverse bias. You can see the characteristics of Zener. The Zener is giving you a VZ of 5 volt here, 5 volt, right? And here it is giving you a VZ of 0.7, right? Okay. Now again, same thing. Current always flows from plus to minus. So what is the direction of current now? The direction of current is in the opposite. It is in the opposite. So you have a Zener here, Zener. Now the direction of current is like this, opposite. So plus minus, plus minus. Now tell me, what voltage will you give? What voltage will you give to the Zener? Is it, see here, when the current is flowing, who comes first? You have to see. The anode comes first, cathode later. It is going from anode to cathode. Again, it is going from anode to cathode. Who comes first? Anode to cathode. Anode to cathode. Anode to cathode means 0.7. Cathode to anode means Vz. So anode to cathode, so it is 0.7. So lower one will give 0.7, upper one also will give 0.7. Are you getting? Now, give me a KVL round the loop, KVL. KVL, you can have a KVL here. 0.7 plus 0.7 plus V naught equal to 0. So your V naught is going to be minus 1.4 volt. Your V naught is going to be minus 1.4. So the Zener, both the Zeners are here, or you can do like this. Minus terminal is connected to cathode, right? Whenever the negative terminal is connected to cathode and the positive terminal is connected to anode, then the diode is what bias? Forward. Then the diode is forward bias. Are you getting? The diode is forward bias. When the diode is forward bias, then the Zener is going to give chota voltage in forward bias, right? And what if the Zener is, I mean, if both Zeners are not there, suppose if both the Zeners are not there, what will be V naught? Your V naught would have been minus 12 volts. So from minus 12, the moment you connect a diode, it became forward. So instead of minus 12, it is giving you minus 1.4. It is going to give you minus 1.4. So the Zener is stopping, right? So once the diode is on, the voltage across the Zener is going to be 0.7 and 0.7. So 0.7 plus 0.7 is going to be 1.4. 1.4. And what is the difference now? The difference is going to be dropped in the resistor, current limiting resistor, right? So whatever the difference is there, suppose here 5.7. What is 12 minus 5.7? What is 12 minus 5.7? What is 12 minus 6? It is 6, is it not? So 6.3, around 6.3 volts is dropped across the resistor in this case. In first case, 0.7 volts. How much is dropped across the resistor? Here there is a drop of 0.7 in the first case. Here there is a 12 volt input, and 11.3 is dropped across the resistor. So 11.3 by 1K, 11.3 milli. 11.3 milliampere of current is flowing. Are you getting in the first case? Okay. Now this is 8 volt positive. So the current goes from plus to minus. But what is the guarantee that the Zener will go to breakdown or not in breakdown? How do we know, right? First, we will calculate VOC. VOC. What is VOC? The open circuited voltage there. Let Zener open circuit Zener, and calculate VOC. If VOC is greater than VZ, suppose the voltage at VOC is 1 volt. The voltage at VOC is 1 volt. Can you have 5 volt Zener going on here? Because this Zener breakdown voltage is 5. Am I right? The Zener breakdown voltage is 5 volt. So if VOC is 1 volt, can you get 5 volt there? It's not possible. Suppose if VOC is 7 volt, between the 2 points, if there is 7 volt, then the Zener will go to breakdown. If VOC is greater than VZ, then the Zener in breakdown. So let's calculate now. Eight volt, 1K, 1.2K. This is VOC. VOC or V naught, right? So what is VOC by voltage division? 8 into 1.2K by 1K plus 1.2K. 2.2, 2.2, 12 8s are. So this is around 4.3 volt. This is around 4.3. But how much is needed for Zener to go to breakdown? 4.3636, right? 4.3636. Himanshu, thank you. So 4.3636, right, is VOC. So if VOC, because VOC is less than VZ, right? This VOC is less than VZ. That means the Zener is not in breakdown. So VOC is less than VZ. Therefore, Zener is not in breakdown. Tell me, if Zener is not in breakdown, it is replaced by open switch. It is replaced by open switch. Then what is V0? V0 is going to be VOC equal to 4.3 volts. So this is a gate problem. So the Zener is off. The Zener is off. You have to be very careful. See, simple. Forget about 1.2K, 1K. What if both are 1K, 1K? That is easy, no? If this is 1K and this is also 1K, what will happen if both are 1K? 4 volt will be there because of voltage. With 4 volt across 1K, can you have a Zener to go to breakdown? Because Zener voltage and this voltage both are same. Are you getting? This 1.2K is across Zener. So the Zener voltage and 1.2K resistor voltage both are same. If instead of 1.2K, if it is 1K, 1K in the series arm, 1K in the shunt arm. So the Zener is going to be across that 1K, only 4 volt, right? So Zener will not go to breakdown, right? Then I have changed the gate problem in this fashion, right? In this fashion. So what did I do now? Instead of 1K in the series arm, I put only 200 ohms. I put only 200 ohms, a small modification of the gate problem. So here what will happen? If it is 200, 8 volt, 200 ohms, 1K. Now what is your VOC here? VOC. VOC or V0? VOC equal to 8 into 1K by 200 ohms plus 1K. So 8 by 1.2K. What is 8 by 1.2K? 12. Eight by 1.2K. How much? 6.66. Okay, 6.66 volts. Good. So 6.66 volts. Now VOC here is greater than VZ. VOC here is greater than VZ. So if VOC is greater than VZ, then Zener is in breakdown. Zener is in breakdown, right? So if Zener is in breakdown, what is the voltage of Zener? Small voltage or big voltage? It is going to be a big voltage, right? Big voltage of 5 volts. 5 volts. So now your V0 is going to be 5 volt. Your V0 is going to be 5 volt, or you can replace Zener like this with a source like this. The Zener is replaced by a source, right? 5 volts. So Zener will give you 5 volt in reverse bias, large voltage in reverse bias, small voltage in forward bias. So Zener is now in reverse bias, so definitely it is going to give you 5 volt, right? Now tell me what is VOC in this case? What is VOC in this case? VOC. With 8.7 volts here, can't you get 0.7 drop? Yes or no? If you open circuit Zener, naturally you get 0.7, right? So now what is VOC? First of all, what is the current I? The current I is going to be 8.7 minus 0.7 by 1K plus 1K. 8 by 2, 4 milliampere. 4 milliampere of current. What is VOC? VOC is going to be I into 1K plus 0.7 volts. So the drop here, the voltage VOC from here to ground is going to be the resistor drop plus the diode drop. So 4 milli into 1K plus 0.7, it is 4.7 volts, 4.7. But how much Zener needs? How much Zener needs? Zener needs at least 5 volt. Yes or no? Zener needs at least 5 volt. So what will happen? The Zener VOC is less than VZ. VOC is less than VZ. Therefore, Zener is off. Zener is off. If Zener is off, it is replaced by an off switch. An off switch. So we are checking one diode at a time. Is it not? So who will get on easily? Out of Zener and diode, who will get on easily? 0.7 is needed for diode. So diode will get on. Yes or no? But Zener in reverse bias is on at least if the VOC is 5 volt. So now your V0 is going to be VOC is going to be 4.7 volt. 4.7 volt is the answer. So the input here is 8.7. 8.7 minus 0.7 by 2K. It is around 4 milliampere. 8 by 2, 4 milliampere. 4 milliampere into 1K plus 0.7, 4.7 volts, right? Or you can do like this, 8.7 minus drop. 8.7 minus drop. What is the current here? 4 milliampere. 8.7 minus 4. Like that you can do. What is VOC? If you apply Kirchhoff's law here, 8.7 minus drop. 8.7 minus 4 milli into 1K. 8.7 minus 4 is going to be 4.7. It is going to be 4.7 volt, right? So the Zener is not in breakdown, right? Sketch the transfer characteristics. VZ is 5 volt. VD on is 0.7. Whenever I say transfer characteristic, my Vin ranges from minus infinity to plus infinity. Vin ranges from minus infinity to plus infinity. V in ranges from minus infinity to plus infinity. Now, the same problem, I will replace a diode with a Zener. Sketch the transfer characteristic. I am going to replace the diode with a Zener. The input ranges from minus infinity to plus infinity. Sketch the transfer characteristics. Now this transfer characteristic we have already drawn in the class for a diode. All right. Now for this I am going to put a Zener across. Okay. Now, if a diode is in this fashion, then a diode is on for V in greater than 0.7 volts. Am I right? But if a diode is in this fashion, we know that a diode is on for V in less than minus 0.7. V in less than minus 0.7 because the diode needs a drop of 0.7. Or I told you for positive cycle, you can put an arrow like this, like this. So can current flow from cathode to anode in a normal PN diode? No. The diode is what bias? Reverse. But if the current flows in this direction, the diode is forward. So for all V in less than minus 0.7, the diode is forward bias. The diode is forward bias. And what is the output? This is the direction of current. So you can apply KVL. KVL, right? Plus 0.7 plus V naught equal to 0. Your V naught is minus 0.7. So for all V in less than minus 0.7, your V naught is going to be minus 0.7. Now, if a diode is not forward, then it is reverse. It is not like a Zener, is it not? Diode has only two states. If it is not forward, it is going to be reverse. For V in less than minus 0.7, if it is forward, what happens when V in is greater, a large positive voltage? If you give positive voltages, then the diode is going to be reverse. For all V in greater than minus 0.7, the diode is forward. Sorry, the diode is reverse. If you give any positive voltage, the diode is reverse. A reverse bias diode is replaced by open switch. A reverse bias diode is replaced by open switch. Then your output follows input. So what is output following input? Y equal to mx. Y equal to mx, where slope m is 1. Slope m is 1. So this slope 1 for V in greater than minus 0.7. But for V naught equal to minus 0.7, this is like y equal to constant. What is y equal to constant? It is a straight line parallel to x-axis. So we are going to take V in on x-axis, V naught on y-axis. V in on x-axis and V naught on y-axis. Now tell me what happens for V in less than minus 0.7. For V in less than minus 0.7, your V naught is going to be minus 0.7, always minus 0.7. Any value less than minus 0.7 you give is going to be minus 0.7. But for V in greater than minus 0.7, it is going to have a slope of 1. It is going to have a slope of 1. So this is the transfer characteristics. So for any V in greater than minus 0.7, the diode is forward. You are going to have a slope of 1. Reverse, you are going to have a slope of 1. For V in less than minus 0.7, the diode is forward and your V naught is restricted to minus 0.7. Now, Zener has got one extra quality. Wow, what is that extra quality? Instead of just an open switch, Zener can also give you a bada voltage, big voltage in reverse bias, and of course a small voltage in forward bias, right? So what is the extra thing that you are going to change in this characteristic if it is a Zener? What change you can bring in this characteristic? What change you can bring in this characteristic so that the Zener is, if I replace the diode with a Zener, what change can you make in the characteristic? Tell me. If you have a diode, if you have a Zener, then during positive cycle, the current will flow in this direction. This is positive cycle, positive cycle. During positive cycle, you're going to have 5 volt. Vz. This is the negative cycle. So when the current flows in this direction, it is going to be, this is positive cycle. This is negative cycle. So when the current flows from anode to cathode, you are going to give 0.7 volts. You're going to give 0.7. So Zener has got one extra quality. What is that extra quality? If your Vin is less than minus 0.7, the Zener is forward bias. If the Zener is forward, then your V0 is going to be minus 0.7. Minus 0.7. What happens in positive cycle? In positive cycle, when your Vin is greater than 5 volt, if your Vin is greater than 5 volt, then your VOC here is also going to be greater than 5 volt. Then the Zener is going to conduct. The Zener is reverse bias. If the Zener is reverse bias, what voltage will a Zener give? Polarities will come only with the direction of current. This is the direction of current, and the Zener is going to give you 5 volt. V0 is 5 volt. So what happens in between? If your Vin is between minus 0.7 and 5, what happens? If your Vn is between minus 0.7 and 5, it's greater than minus 0.7, but it's less than 5, then the Zener is off. So this is something I told you, if the Zener is off, it is as good as a PN diode. So it is like off from minus 0.7 to 5, it is like off. Once you increase more than 5, it goes to on. So now your output follows input. So just see the previous diagram and this diagram, previous characteristic, the previous characteristics and this characteristics both are same, except for the fact that tell me, for all Vn less than minus 0.7, your V0 is minus 0.7 volts. So your V0 is minus 0.7. So same characteristic we got, same characteristic. Then after that, between minus 0.7 and 5 volt, you are going to have y equal to mx, same characteristic. Can you see? Same characteristic we got till 5 volt. But when Vn crosses 5, then your output is restricted to 5. Your output is restricted to 5. Can you see? The small change that we have got here is when Vn is going greater than 5, then your output is restricted to 5. But if your Vn is less than minus 0.7, the diode and Zener both are same in forward bias, right? But diode, once it is off, finished, it is off forever. But Zener will not be like that, right? When you keep on decreasing your voltage or increasing your voltage, the Zener will keep on seeing, even in reverse bias, will I get a Vz of 5? So once he gets a Vz of 5 in the positive direction, the Zener is going to go to breakdown and the output is restricted to 5 volt. The Zener diode has got one extra quality, only one extra quality, that it works in reverse bias and it gives a larger voltage, right? So this is a normal PN diode characteristic. The Zener characteristic is one portion extra. Now, what about this circuit here? So I told you first we have to calculate here VOC. VOC. What is VOC here? Your VOC is going to be V in by 2. Your VOC is going to be V in by 2. So the Zener will get only V in by 2 here. So once you connect the Zener here, it is going to get only V in by 2. So if this VOC is greater than 5 volt, then your V0 is going to be 5 volt. The Zener will go to breakdown. The Zener in breakdown. The Zener in breakdown. But what is VOC? What is VOC, by the way? VOC is going to be V in by 2. V in by 2 is greater than 5. That means you have to wait V in till it touches 10 volt this time. In the previous transfer characteristic 5 volt, but now because of voltage division, if your V in is greater than 10, then your V0 is going to be 5. Case 1. Next, let me change the direction of arrow now. This is positive. Now I am going to change the direction of arrow, right? This is negative cycle. So when I change the direction of arrow, when do you think this diode should be on, right? This diode will be on when VOC is less than 0.7. If VOC is less than 0.7 in the negative direction, minus 0.7, then your V0 is going to be minus 0.7. But VOC is nothing but V in by 2 should be less than minus 0.7, or your V in should be less than minus 1.4. Minus 1.4 for your output to be minus 0.7. But if V in is between minus 1.4 to 10 volt, if your V in is between minus 1.4 to 10 volt, then the Zener is off. If the Zener is off, you have to replace it by open switch. Then your output is V in by 2. So for the first time, we have got a slope M. The slope M equal to 0.5 this time. Slope M equal to 0.5. And here, Y equal to constant. Y equal to constant is a straight line parallel to x-axis. So how are you going to draw the transfer characteristics now? You can take V in on x-axis, V0 on y-axis, till your V in touches minus 1.4 volt. Your V in should be minus 1.4. Your V0 will be minus 0.7. What happens when V in is less than minus 1.4? Your V0 is restricted to minus 0.7. Am I right? And then after that, between minus 1.4 and 10, when V in touches 10 volt, your V0 is touching 5 volt. The slope M is 0.5. If V in is greater than 10, then your output is restricted to 5. So now the characteristics is kind of slightly stretched here. In the previous case, you have to give a voltage which is 5 volt input for 5 volt, right? The output, anything greater than 5, your V in greater than 5, your output is restricted to 5. Hey, if your V in is less than minus 0.7, your output is restricted to minus 0.7. But because of an extra resistor, the voltage divider here, if your V in is greater than 10 volt, then only your output is going to give you 5, right? If your V in is less than minus 1.4, then only you are going to get a 0.7 drop in the negative direction, right? So the slope here is 0.5, right, in the middle. Now for the diode and this 2 volt, we have already drawn the characteristics. Now tell me, if I have a diode and 2 volt here, 2 volt, when is a diode forward bias? Is it during the positive cycle or is it during the negative cycle? Tell me, when is a diode forward? Is it during positive cycle or is it during the negative cycle? Tell me, out of these two, who gets forward bias in positive and who gets, in my opinion, during positive cycle, the diode is going to get forward. Who is going to get forward? The diode, but not the Zener, because who is easy to get forward? This is 0.7 and 2, you need only 2.7 volts at input. But can a diode get forward in the negative cycle? Can a diode, PN diode, get forward in negative cycle here? No. So the current cannot flow like this, right? No. But the current will flow like this. So who is lucky in the negative cycle? Who is lucky in the positive cycle? In the positive cycle, you will have a drop of 2.7. This is positive cycle. This is negative cycle. In the negative cycle, who is lucky? The Zener is going to get on. Zener on in negative cycle. But because the current is flowing from anode to cathode, this poor Zener cannot give Vz. It is going to give only 0.7 volts. 0.7 volts it is going to give. The Zener is on in the negative cycle. It is going to give only 0.7 volts. So during positive cycle, who is on during positive cycle? Because if you think that in positive cycle, the Zener is on, then the voltage here across this should be 5. But with 5, the diode will also be on. Then you are violating Kirchhoff's law. You are violating Kirchhoff's law. So who is on and who is off? The diode is on first, not the Zener, right? Or you can think like this. Suppose you have given a voltage here, Vin, which is a sine wave, suppose. When the sine wave is slowly increasing, who comes first? 5 volt comes first or 2.7 comes first? 2.7, naturally. So when your input is 2.7, then the diode is going to get on. So once the diode is on, the output is clipped at 2.7 because the voltage here is going to be 2.7. The Zener is not lucky in the forward bias. But the Zener is when the current direction is reversed in the negative cycle of input, then for negative cycle of input, the Zener is going to get on and it is going to give you 0.7 in the negative direction. Are you getting right? In this direction. Okay, so what is the solution now for this? For all Vin greater than 2.7, the diode is on. Diode on. The diode is on, right? When the diode is on, you're going to have 0.7 here and 2 volt here. This is V0. Should I apply KVL now? Not needed. It is simply 2.7 volts. 0.7 plus 2 is 2.7. Now what happens in the second case when Vn is less than minus 0.7? If you go in the negative direction, PN diode is not going to get on. The Zener is going to get on. If Vn is less than minus 0.7, the Zener is on. Zener is on. So this is Vn negative. Negative. So just see if this current flows in this direction, this is a polarity, and here you have V0. Now you can apply KVL. Apply KVL now. 0.7 plus V0 equal to 0. Your V0 is minus 0.7. So it means that if current flows in the opposite direction, your V0 has to be minus 0.7. Your V0 has to be minus 0.7. So what is a transition now? What is a transition? Above 2.7, diode is on. Below minus 0.7, Zener is on. So what happens when Vn is between minus 0.7 and 2.7? Right? So if it is less than minus 0.7 and greater than, if it is less than 2.7 and greater than minus 0.7, what will happen? If your Vn is between minus 0.7 and 2.7, then the diode is off and Zener is also off. Diode off, right? Zener is also off. So then your output follows input. So this is like y equal to mx. Its slope m equal to 1. So how are you going to draw the transfer characteristics? Transfer characteristics. For all Vn greater than 2.7, for all Vn greater than 2.7, for all Vn greater than 2.7, the output is restricted to 2.7. Am I right? For all Vn less than minus 0.7, the output is restricted to minus 0.7. Between minus 0.7 and 2.7, it is y equal to mx. It is y equal to mx. So this is the transfer characteristics. This is the transfer characteristics. So let me repeat, during positive cycle, PN diode is on if Vn is greater than 2.7, and Zener is on both in positive as well as negative. But in positive, there is no scope, because once the diode is on, finish, the diode will not listen to anyone. He says, I am 0.7, that's it. The diode across voltage, come what may, it is going to be 0.7. Can you change this 2 volts to 5 volt? Is it DC voltage? It is always 2. Can you change the diode drop? No, it will always be 0.7. 0.7 plus 2, 2.7. Diode Zener has no scope. Zener needs at least 5 volt. There is no scope for Zener to get on in the positive direction, right? But in the negative direction, obviously the diode is off. But the Zener can conduct both in positive as well as negative. And unfortunately, this Zener is getting only 0.7 because the current flows from anode to cathode, not from cathode to anode. The current has to flow from anode to cathode. This is positive cycle, this is negative cycle. But if you want a Zener to give you a characteristic that is same between in the positive and same in the negative. Suppose I want Zener to give here 5 volt and 5 volt, or 5.7 volt here and 5.7 volt here. Then what you should do? Such a Zener is, you can get such a Zener by combining two Zener diodes. You take two Zener diodes connected back to back. This is a great idea, right? If you connect them back to back, what will happen if the current flows in this direction or in this direction? What will happen if the current flows in this direction? The upper diode gives 0.7 and the lower diode gives 5. What happens if this flows in this direction? The lower diode gives 0.7, but the upper diode gives 5. So combining, if you want same breakdown voltage in positive and negative, a single Zener will not do. A Zener diode should be combined with another Zener, and that package you can use it as a Zener, a composite, like a Darlington pair, which is a composite transistor. This is like a composite Zener pair. If you use this pair, then it will conduct for positive cycle and give 5.7, conduct for negative cycle and also give 5.7, right? Minus 5.7. So tell me, what is the behavior of this directly? V in greater than 5.7, V in greater than 5.7, your V naught is 5.7. For V in less than minus 5.7, your V naught will always be minus 5.7. Because here the voltage is 5.7, here the voltage is minus 5.7. If your V in is anywhere between minus 5.7 and plus 5.7, your V naught is going to be V in, right? V naught is going to be V. So how will the transfer characteristics look like? Nicely, you are going to get a line. The moment V in is 5.7 volts, finished. Upper diode will give 0.7, lower diode will give 5. Output is restricted to 5.7. If in the negative direction you give minus 5.7, then the lower diode will give 0.7, upper diode will give 5 in the opposite direction. Your output is restricted to minus 5.7. So if you want same breakdown voltage in positive and negative direction, what is the technique? You have to connect two Zeners back to back. If you connect them, then you are going to get a clean transfer characteristics like this. So if you give even a sine wave, we have done some clipping circuits, do you remember? What happens if you give a sine wave for this, a sine wave as the input? As the input, then it is going to act like a double bias clipper. So once you give a voltage anywhere between minus 0.7 and plus 0.7, your output and input both are same. Your output and input both are same. Output and input both are same. But if you give a voltage greater than 5.7, your output is restricted to 5.7. If you give a voltage less than minus 5.7, the output is restricted to minus 5.7. So your output follows input only between 5.7, minus 5.7 and plus 5.7. So these two, you can use it as a single Zener, and this Zener can conduct both for positive as well as negative, right? So some books, they draw this circuit, this Zener like this. Like this. Are you getting? This is Zener connected back to back. So this looks something like, Shiv Ji ka, I don't know what you call that, right? Yeah, Shiv Ji ka Damru, right? Damru, yeah, very good. So whenever there is a Damru in the circuit, so remember that it is going to give you the same voltage in positive and the same voltage in negative, right? Because if the upper one is forward, the lower one will be reverse. If the lower one is forward, the upper one is reverse. So the net voltage is always going to be same, right? So the net voltage is always going to be same. Okay. Now let's include this is a Zener characteristics. Now I'm going to include something called the so what do you call this, right? So what do you call this? Somebody is sitting in a chair, right? Like this. I don't know how to draw. With a laptop here. Yeah, this is me, okay? Now we call here this is a knee. Oh, my head gone cross. Don't worry, I'm very bad with drawing. So this is something called the knee, right? The minimum current required for the Zener to be on, right? That's called the IZ knee. It's called IZ knee, right? So what is a knee current? The knee current is the minimum current required for the Zener to be on. Knee current is a minimum current required for Zener to be on. Now, what if the current is less than knee current? If the current is less than knee current, then this voltage here is going to be less than Vz, right? If the current is still less than that, it's going to be still less than Vz. Are you getting, right? So at least you need how much a knee current for the Zener to be on, right? So knee current is the minimum current required for Zener to be on, right? And what is IZ max? IZ max is the maximum current Zener can safely handle. So it's the maximum current Zener can safely handle is the IZ max. So knee current is a minimum current required for Zener to be on, right? Now, on the same token, if I say that find V in minimum for the Zener to be on. Find V in minimum for the Zener to be on. I have V in here. and of course my Vz is how much? 5 volt. But it will give 5. It will give 5 only when there is a minimum current of what current? Knee current, right? 1 kilo. So find V in minimum for the Zener to be on. A bit is if your Iz knee is 1 milliampere, 1 milliampere. B bit is the Iz knee is if it is 10 milliampere. So find V in minimum for the Zener to be on. Zener to be on. If the knee current is 1 milliampere, and what happens if the knee current is 10 milliampere? Now, if you are able to solve this problem, then the next gate problem is just a motivation, right? So if you are able to solve this problem, then the next gate problem which I'm going to give you will be much easier for you, right? So find V in minimum for the Zener to be on, right? So here at least Iz, because this current Iz and Is and Iz both are same, am I right? Because this is a series circuit. So what is V in KVL? KVL. The KVL says that minus V in plus Iz into 1K plus Vz, which is phi equal to 0. So what is V in? It is Iz into 1K plus phi. Plus phi. But at least a knee current of 1 milliampere should flow. If Iz is Iz knee of 1 milliampere, then V in minimum is going to be 1 milliampere into 1K plus 5. It is 6 volts. 6 volts should be there. If you give a voltage less than 6, then the Zener will not go to on. So suppose you give 5.1. 5.1. Now what happens if you give 5.1? Then this 5.1 minus some voltage divided by 1K, the current is very small, right? So that current is not sufficient for the Zener to go to what region? Breakdown, right? So if the Zener has to go to breakdown, then it has to give a voltage, because Zener can be from an open circuit all the way till how many volts? 5. So if it from the open circuit it has to come down to 5, then once it comes to 5, at least a knee current of 1 milliampere should be there. So if it has to be 1 milliampere, then you need 6 volts at least, right? Okay. But what about B bit? B bit says that if my Iz knee is 10 milliampere, then V in minimum is going to be Iz into 1K plus 5 which is 10 milliampere into 1K plus 5, at least 15 volt you should give. At least how many volt you should give? 15 volt, then only the Zener will be on. So what is the learning in these two problems? Who is going to get on first? Who is going to get on first? The one which demands less knee current or the one that demands more knee current? Who will get on? The one that demands more knee current or the one that demands less knee current? Naturally, the one that demands less knee current. See, because when slowly, suppose this is a variable source, suppose this is a variable source, and slowly you're increasing V, slowly. As voltage increases, current should increase. Voltage increases, current should increase. Ohm's law. But who will get on? The Zener, suppose two Zener are there. One Zener knee current is 1 milli, the other Zener is 10 milli, and the same voltage is given to both. So who is going to get on first? The one that demands less knee current is going to get on. Is it not? Because by the time 10 milliampere flows, the Zener of 1 milliampere would have already been on. So with this simple idea, tell me a gate problem is given, a gate problem where the examiner is very clever. The examiner has given two Zeners. Say each one, VZ1 is 5 volt, VZ2 is also 5 volt. Both are 5 volt. And here he has supplied some voltage here, which is say 0 to 8 volt, right? Some 8 volt max. And he put this symbol. What does this symbol mean? This symbol means it is variable. The way slowly you are increasing from 0 to 8. When you increase from 0 to 8, he says, what is this V1 and V2? What is this V1 and V2? And he has given IZ1 equal to, or IZ1 knee equal to 3 milliampere, and IZ2 knee equal to some current 1 milliampere. And now he says find V1 and V2. Find V1 and V2. Right? And 4 options were given. A, B, C, D. 4 options are given. First option is V1 equal to 5 and V2 is also 5. Second option, V1 equal to 4, V2 is 4. Third option, V1 equal to 3, V2 equal to 5. Fourth option, V1 equal to 5, V2 equal to 3. So 4 options are given, right? The examiner says that he's slowly increasing, that's a variable voltage. Slowly, who will get on first, right? Or what is the voltage V1 and V2? He says, what is the voltage V1 and V2? You are increasing from 0 to 8 volts. So once you reach 8, what will happen? Who gets, right? Who gets 5-5 or 4-4 or 3-5 or 5-3? What is the right answer? Right? It's a gate problem. Think about it. See, the reason I have given you options is so that you can just type A or B or C or D like that, right? Okay, right? Now, let's check each option. Now, please, the examiner didn't say V1 and V2. What he says is, find the possible voltage V1 and V2. So he said, find the possible voltage. What do you mean by find the possible voltage V1 and V2? It means that out of 4 options, 3 options are not at all possible. However you try, however you think, 3 options are literally wrong. Find the possible answer. So why the 4th option is right? Because the other 3 are wrong. The 3 options are utterly wrong here. That is why the leftover option can be the possible answer. Are you getting? Find the possible answer. Find the possible voltages or find the possible answer. Are you getting? Find the possible answer. Right? Now, so you are not here to identify right answer, please. You are here to identify 3 wrong answers which are never possible, right? Let's see one by one. First, A bit. V1 is 5, V2 is 5. What is 5 plus 5? 5 plus 5 is 10 volt. When source is 8 volt, can you get a 10 volt drop? A is wrong. A is wrong. Wrong. Because if source voltage is 8 volt, we cannot get 10 volt drop. 5 plus 5 is 10. So this is utterly wrong. Are you getting? This is utterly wrong. In Telugu, they call this option as Neralu Goralu, right? So this can never happen. However you try, this can never happen. A is never possible, right? What is B? B is 4 volt here and 4 volt here. When both Zenars, if they are nonlinear, will give you the same 4 volt, provided their characteristics are same. Suppose one Zenar has a characteristic like this, the other Zenar has got a characteristic like this. There's a Zenar which needs 3 milliampere of current. There's a Zenar which needs 1 milliampere of current. Are you getting? So 3 milli and 1 milli, these characteristics are totally different. They are totally different. We don't know who is 1 and who is 2, but I'm just saying examiner given, right? 1 milli and 3 milli. So when the characteristics are different, how they can give same voltage, right? Characteristics are different. So V1 is not equal to V2, right? See, V1 is 3, V2 is 5. V1 is 3 and V2 is 5. Now slowly I'm increasing this. When I'm slowly increasing this, what current will flow? What current will flow? 0 milliampere, 0.5 milliampere, 1 milliampere. Which current will come first from source? As you are slowly increasing, who comes first from source? Naturally, the source is going to give you a current of 1 milli first. After that 2 milli, after that 5 milli. So when 1 milliampere flows, which diode is going to get on when 1 milliampere flows in this loop? Which diode is going to get on? Naturally, V2 will be on. Is it not? Because what is IZ2? 1 milli. So your V2 is going to get on. Once V2 gets on, right, this will be 5. And when you reach 8 volt, if this is 5, the leftover voltage will be V1, no? Yes or no? Why D is wrong? Okay. Why D is wrong? V1 is 5, V2 is 3. That means they are saying that for the same current here, for the same current, Zener Z1 is on, but Z2 is still not on. How can Z2 not on? Just because it is upside down. Say in series circuit, same current will flow. Who will get on first? In a series circuit, remember how many currents will flow? Same, 100 currents will not flow. Same current will flow. So when same current is flowing, who is going to get on? Naturally, the one with a less knee current. So slowly you are increasing. As you are increasing, which diode gets on? Which diode will say first thank you? 2 diodes are waiting, right? Slowly you are increasing current. 0 milliampere, 0.5 milliampere. Which diode will say thank you very much first? The one that needs less knee current. So the one that needs less knee current, so is Z2. Z2. What is IZ2? 1 milliampere. So he gets 5 and V1 is going to be 3, right? But D bit says that V1 is 5, V2 is 3. That means V1 has already got 3 milliampere and V2 is still not got. See, it's almost like you are giving 30,000 to a person and that person is saying that you have not even given me 10,000 rupees. You have given 30,000 to a person, right? 30,000 is in his pocket. Now that person is crying, not even 10,000 you have given. 30,000 at 3 milliampere current is flowing, and can you say that 1 milliampere didn't flow, right? So when 3 milliamperes is flowing, it is understood that the current has crossed 1 milliampere. So D is also wrong. V1 cannot be on first. V1 cannot be on first as the knee current is large. How much is IZ knee? 3 milliampere. So what is a possible answer now? What is possible answer? The possible answer is C. Okay, please give me a current that is between 1 milli and 3 milli. Give me because if 3 milli flows, both would have been on, no? Is it not? That will happen only when Vin is more than 10 volts. So give me a number between 1 and 3. Just some random number between 1 and 3. Simple number is 2. Is it not? Simple number is 2. So let me put a line here and see where it will intersect. 2 milliampere. So 2 milliampere, it has intersected at 2 points here, right? Now let me draw a line here. If this is 5, this should be 3, no? Anything less than 5. Anything less than 5. So which characteristics has got 5? Which characteristics has got 5? Which characteristic? The one that with a less knee current. This one is less. So who is less knee current wala here? VZ1, right? So this is Z1 characteristics. So this one is Z1 characteristics. This one. And this one is going to be Z2 characteristics. So Z2 characteristics will give you 5 volts only when 3 milliampere flows. But when 3 milliampere flows, then both should have both are on. When both are on, the voltage should be 10 drop. That means your input should be more than 10. Yes or no? If your input is more than 10, then only both are going to get on, right? So that is not possible. So which is a possible answer now? Who gets simple, sir? From the previous diagram, who gets on first? The one with less knee current. That's all. Who is having less knee current? Less knee current wala is Z2. So where is Z2 here? Z2, Z2, Z2 here. Where is Z2? 5 volt. Z2 is 5 here, right? Less knee current. So C is the right answer. C is the right answer. So when you have 8 volt here, 8 volt, there is a possibility that this current is less than 3 milli or greater than 1 milliampere. So if it is less than 3 milli and greater than 1 milli, just an assumption, right? If it is greater than 1 milli and if it is less than 3 milli and greater than 1 milli, who is going to get on, right? Z2 is 1 milli, right? Z2. So this fellow would have been 5. This fellow would be 3. Are you getting? So 3 and 5, right? Anywhere in between. Now, if you say, no, sir, how do you know it is between 1 milli and 3 milli? Who told? Huh? There is no such question. How are you making an assumption? Simple logic. If it is less than 1 milliampere, then what would have happened if it is less than 1 milliampere? If the current is less than 1 milliampere, then both are off. Both are off. They are giving less than 5. But how can you expect 4, 4? Are they same characteristics to give 4, 4? It's not possible. If it is 5, 5, that is cheating. With 8 volt drop, you cannot get 10 volt. With 8 volt input, you cannot get 10 volt drop. Are you getting? Then what is the possible answer is simple logic. Final logic is what? The one with less knee current is going to get on. That's all. The one with less knee current is going to get on, right? Okay, we'll take a break now. When we come back, we will see, right? Let's take a break. So who is having less knee current? Less knee current is Z2. Z2. This is Z2. Z2. Z1. Less knee current wala is Z2. Z1. Good. Okay, we'll take a break. One more thing here. When there is a non-linear characteristic, some current will flow. Are you getting? Some current will flow. Don't think if this is not piecewise linear to say completely current off. Some current will flow even for 0 plus some current will flow. Some current will flow. Some current will flow. That is the non-linear. Some little leakage, some current is going to flow. That is what the characteristic says. This characteristic says that you will never have zero current, right?
Hello.
Okay. Fine. Can you hear me? Can you hear me? Can you hear me?
Yes, sir. Audible.
Okay, so in the previous characteristics, we have seen that there is always some current flowing. Are you getting? There is always some current flowing. One diode is like this. There is another diode like this. So there is one diode which needs 1 milliampere. There is another diode which needs 3 milliampere. But even if it is 0.1 milliampere, suppose there is 0.1 milliampere, you realize that the diode with less knee current is always greater than the diode with more knee current, right? The diode with more knee current is always giving you a drop which is less than this. Suppose this is 5 volt and there is one guy with say 1 volt. There's the other guy with 0.5 volt, right? for 0.1 milliampere. Suppose if the current is 0.3 milliampere, then this is like 2.5 volt. This is like 1.1 volt. So at any instant of time, if you see who is having a greater voltage, the one that with less knee current is always having a greater voltage across it, right? So you have two here. So the lower one, so for any current, 0.1 milliampere, for 0.3 milliampere, for 0.5 milliampere, any current that flows, always at any instant of time, we have seen that VZ2, this is VZ1. This one has who has less knee current here? Z2 has less knee current. This one is Z2, this is Z1. So we can see always that this voltage is not V2, this is V1. Always V2 is greater than V1. Always V2 is greater. You take any current because the characteristics is linear or non-linear. But if the characteristics is piecewise linear, then finished. 3 volt and all you will never get. You will get only 5 volt. That's it. It is either 5 volt or 0. It is either 5 volt or it is 0, but it cannot be 3 volt to 2 volt like that. It's not possible. So when can you get 5 or even less than 5 also if the characteristics is non-linear? The characters you can just keep drawing like this. Take a scale, draw and take 2 points and see the intersection. At any instant of time, the one with less knee current is going to get what? On, right? The one with more knee current, is not giving you that much voltage because the characteristics is non-linear. Right? Okay. So if you have a doubt, then you have to draw the characteristics and see for yourself, right? Okay. Given Zener ideal with Vz equal to 4 volt and Vd on equal to 0. So what do you mean by an ideal characteristics? Ideal diode characteristics is like this. This is an ideal diode characteristic. So it will give voltage 0 in forward bias and reverse bias it is giving 4 volt. It is going to give 4 volt only in what bias? Reverse bias, right? In forward bias, it is going to give you 0 volts, right? So sketch V0. Sketch V0. So this is also a gate problem. Sketch V0. Sketch V0 if Zener is ideal. Given Zener ideal with Vz equal to 4 volt. Okay, so this is a gate problem. Now to solve this, you can have a normal PN diode first, a normal PN diode, because Zener has got only extra this line. This line is a extra characteristic. Otherwise, what is the characteristics of these two portions? This and this, these two portions. This is an ideal characteristics of any diode, any diode. So if this diode is ideal, then what will be your V naught? What will be your V naught? So this is your input. What will be your V naught? During positive cycle, the diode is reverse bias, reverse bias. During negative cycle, the diode is forward bias. Diode is forward bias, right? During positive cycle, the diode is reverse bias. During negative cycle, the diode is forward bias. So a Zener also behaves in the same fashion. There is no difference. But extra quality of Zener is, once you give a voltage greater than 4, then he will start behaving as a regulator. But otherwise, Zener will behave as an open switch only. In reverse bias, Zener is an open switch. And what is Zener here in forward bias? In forward bias, he is a short circuit, right? He's a short circuit. So Zener and normal diode, both are same, except for that extra characteristics you get once your input crosses 4 volt and the Zener is in reverse bias, right? Okay. So case 1, for all Vin between 0 and 4 volt, the Zener is off. When the Zener is off, what is the output? The output is going to be 0 volts because no current. No current. What happens when Vin is greater than 4? What happens when Vin is greater than 4? The Zener in breakdown. Once the Zener is in breakdown, this voltage is 4 volt. What is your V naught? If you apply KVL, you realize that minus Vin plus 4 plus V naught is 0. That means V naught is Vin minus 4. Your V naught is Vin minus 4. This is for Vin greater than 4. Now what happens in negative cycle? In negative cycle, what will happen, right? In negative cycle, for all Vin negative, the Zener is forward bias. Ideal Zener, ideal diode is forward bias. A forward bias diode is replaced by short circuit and your output follows input. Output follows input. Output follows input. This is like Y equal to mx. This is like Y equal to mx. So your between 0 and 4, your output is 0. For Vin greater than 4, your V naught is Vin minus 4. For Vin negative, your V naught is Vin. So the examiner now wants you to sketch this. Wants you to sketch this voltage, right? So the examiner has given 4 waveforms. Tell me what happens in negative cycle. In negative cycle, your output follows input. Your output follows input. Right? 8 volt. 8 sin t. But in positive cycle, what happens when Vin is greater than 4? Between 0 and 4. Between 0 and 4. What is happening between 0 and 4? Between 0 and 4, there is no output. Between 0 and 4, there is no output. But for Vn greater than 4, what happens when Vn is greater than 4? This portion greater. When Vn is greater than 4, your output is Vn minus 4. That means if Vn is 4, your V0 is 0. If Vn is 5, your V0 is 1. If Vn is 8, your V0 is going to be only 4 volt, right? So when Vn touches 8 volt here, your V0 is going to touch only 4 volt. So some odd figure, right? You're going to get. We don't know what is this, right? Well, because gate exam, 4 waveforms he has drawn, but this is the waveform, something looks like this. For V0 greater than 4, it is going to be Vn minus 4. Between 0 and 4, your V0 is 0. Between 0 and 4, your V0 is 0. And your Vn is V0 is Vn minus 4 for Vn greater than 4. For Vn negative, however, your output follows input, right? If you imagine that this is a Zener diode, right? Otherwise, positive cycle, reverse bias, negative cycle, forward bias, right? Positive cycle, output follows input, negative cycle, the Zener is going to, the diode is going to get on, right? Output follows input. Fine. See, what is expected when I started this Zener circuit, I told you that there is always a range of ripple voltage where Zener will be satisfactorily on. Suppose the load should not be connected here, R. Where should be the load? The load should be across Zener. Are you getting? Across Zener, there should be a load. But gate examiner, he has connected load in series, right? But generally, when you are designing a circuit, the load should be across Zener. And there is always a range of voltage where Zener will be satisfactorily on. Otherwise, Zener is not a good regulator. When you see all this, you realize that is this a good regulator, right? Because a regulator has to give a constant voltage for all input voltages Vin. For all input voltages Vin, it has to give a constant voltage, right? So let's see that range, right? So now we will shift from all these problems to a little practical approach, as to what is the design of a voltage regulator. What is, we have few other parameters to come into picture, right? Rather than just sketching the characteristics and the waveforms, right? So find the range of voltage source Vs to which the Zener is satisfactorily on. If the knee current is 1 milliampere and the maximum current Zener can safely handle is 60 milliamp. Now let's see what should be the range of your voltage source Vs. So accordingly, we have to generate this Vs. Otherwise, if you give sine wave, like in a gate problem, Zener will show all colors, yes or no? Forward bias on, reverse bias off, and then off for some duration, and then it is on. So all this headache will be there. But what is our aim in regulator? Output should always be constant you want, right? So if you want constant, then what sort of input you have to give? What sort of input you have to give? Find the range of voltage source Vs to which the Zener is satisfactorily on. If the minimum knee current is 1 milliampere, knee, and the maximum current Zener can safely handle is 60 milliamp, and it has to give you a 10 volt output. Okay, so let's solve. Can you see here? Suppose if Vs increases slowly, what will increase here? Is will increase. If Vs increases, Is will increase. This Is is split into Iz and IL. Iz is the Zener current and IL is the load current. IL is the load current. So if Vs increases, Is will increase, Iz and IL. It is split. Now, if V0 is constant, then IL is constant. IL constant because V0 is constant. So if IL is constant because V0 is constant, if Is is increasing, who will compensate for that? The Iz will increase. Remember, Iz is going to increase. Whenever Vs increases, where is that extra current sinking? The extra current will always flow through Zener. So Zener should have a wide range where from 1 milliampere to 60 milliampere, where he can be satisfactorily on, and the output will always be at 10 volts. Output will always be at 10 volts. Are you getting? See, this is the reason I remember we have used Zener for protecting some weak sensors. Some weak sensor. Suppose, imagine my sensor is the 1K resistor. Sensor is 1K resistor. Whenever Vs increases, what will happen if Zener is not there? If Zener is not there, right? Initially we had sensors which used to blow very often. Very often they used to blow, again reconnect it, again someday it will blow, again reconnect it. Why is this happening? Because whenever your Vs increases, any source current increases, then naturally the sensor used to blow. Then we found that what happens if we connect a Zener across the sensor? If you connect a Zener across the sensor, because the sensor is meant to drive some digital board, logic 1, logic 0. When the Zener is on, however, it will indicate logic 1. It's not a problem. But if any extra current comes from the source, any extra current, that current is now going to flow through Zener, but the load current will always remain constant. That is why we have used the Zener to protect some weak sensors, right? As a different viewpoint. Because Zener has got this feature that any current that comes from the source will always flow through Zener. The load current will always remain constant because output voltage is constant. Are you getting? Okay. So case 1, let Iz knee equal to 1 milliampere. Iz knee equal to 1 milliampere. Now tell me, what is your Vs minimum? Vs equal to Is into 300 plus Vz. Is into 300 plus Vz. What is Is? Is equal to Iz plus IL. Am I right? So it is 1 milliampere plus, what is load current? What is load current if V0 is 10? It is going to be V0 by 1K, 1 milliampere plus 10 by 1K. It is 11 milliampere. So your Is is 11 milliampere into 300 plus 10. It is going to be minimum 13.3 volt you have to give. You have to give Vs minimum 13.3 volt. That is when the Zener is going to get on. The second case is Iz max is going to be 60 milliamp, 60 milli. Then what is Is? Is equal to Iz plus IL. It is 60 milli plus IL. It is 10 by 1K, 10 milli, 70 milli. 70 milli, right? So what is Vs maximum? It is Is into 300 plus Vz. So there is only one loop, am I right? What is the loop here? Vs is equal to Is into 300 plus 10. 70 milli into 300 plus 10. It is 31 volt. So what is the range of Vs? Vs range is going to be from 13.3 to 31 volt. Vs range is going to be from 13.3 to 31. So if you give a peak detector, a peak detector output is something like this, right? Discharging, charging, discharging, charging, discharging, charging, discharging. But this range should be between what voltage? 13.3 to 31 volt. Suppose if you are able to generate this kind of a voltage from a peak detector, then what will be your output? Your output is always going to be constant at 10 volt. That is why Zener is called a voltage regulator. A voltage regulator. So Zener is called a voltage regulator only with proper input. Yes or no? See, anywhere, in any circuit, input should be proper. Suppose I have generated a nice amplifier, but my input is a large signal. Can it be a linear amplifier? An amplifier is a linear amplifier only when the input signal is kept small signal. So proper input should be there in any circuit. For a regulator circuit, what is the proper input? Just before the regulator, today I have given you the block diagram. Just before the regulator, you should have a proper peak detector. That peak detector output, if it is between 13.3 to 31, then naturally the Zener is going to give you a constant VCC. This is our constant VCC supply of 10 volt. That is why Zener is a good voltage regulator only with proper input. If you give a sine wave like in gate problem, finished. Zener will be open switch, closed switch, yes or no? So your output voltage should always remain constant irrespective of any variation of input voltage. That is why Zener is a regulator. Regulator means what? What do you mean by regulator? Something that will give you a constant voltage is called a voltage regulator, right? It should regulate, is it not? Constant. So this is nothing but our what you call battery. Yes or no? What is the characteristics of a battery? Is a characteristics of a regulator. What is the characteristic of a DC source? Suppose you have a DC source. What is the characteristics? Suppose you have a DC source of V volts, right? This is a current I. This current will change when I change the load. If load changes, naturally current will change. Is it not? I equal to V by R. So when you want to draw the characteristics of a DC source, how will you draw? Though current changes, the voltage should remain constant. How current will change? Based on load. Today, today what is my load? My load is suppose common base amplifier. Tomorrow I want to use the same VCC for common emitter amplifier. Day after tomorrow I want it to use on a common collector amplifier. So my load is changing. When my load is changing, naturally current will also change, but my VCC supply should never change. So what is the characteristics of a good regulator or a good DC source? Even though current changes or even though load changes, I have to give him a constant voltage. The constant VCC should be there. Whatever load you want to connect, Darlington pair, differential amplifier, anything you connect, VCC should always be VCC. That is the characteristics of a DC source or voltage regulator. Because what is voltage regulator? Voltage regulator means it is a VCC supply. Voltage regulator means it is a DC supply. What is the characteristics of DC supply? Though current changes, though load changes, the voltage should always remain constant. That is why it is called a regulator. It is called a regulator. Okay. Now let us design now. Design. In a practical regulator, source, as I told you, is not in your hands. Load also is not in your hand. Just now I told you, one day I might use common base, another day I might use common collector. So one day common base with common collector in parallel. So naturally, the load is not fixed. The load, someday I will not use anything. If I don't use anything, I remove the load, then my current is going to be zero. Suppose my load current, my load is varying from 0 milliampere to 100 milliampere. My load is changing from 0 to 100 milliampere. I have a Zener of 10 volt and my Vs is also changing. Generally in gate problems, only one is variable. But I'm varying two. That means if you are able to solve this problem, you can solve any Zener problem. Any Zener problem is a subset of this problem. Of course, this is also easy only, right? But any Zener problem you solve will be a subset of this, right? Because here I'm going to make a practical regulator where my source is not in my hands, my load is also not in my hand. I have to design this, right? Vs. Say Vs is from 20 volt to 30 volt. 20 volt to 30 volt. So let me design the value of Rs or Rs minimum such that at least a knee current of 10 milliampere will flow through Zener. And Zener is always on. Zener should be always on, right? If it's off, there is no meaning in a regulator. It should always be on, and at least a current of 10 milliampere should flow, knee current of 10 milliampere. The second extreme is, Suppose if you don't connect a load, all the current from supply is going to flow through Zener, no? Then Zener will get heated up. When the Zener gets heated up, then maybe the Zener will blow. So in order to protect the Zener, we have to choose the power rating of Zener. So calculate the maximum power dissipation. Maximum power dissipation. Maximum power dissipation means it is the maximum rating of the Zener. Are you getting? Suppose the power rating of Zener is 1 watt. 1 watt. You have bought a Zener from market of 1 watt. But the heat that is generated, the power dissipation, maximum power dissipation is 3 watt. Then can a 1 watt Zener sustain? Zener will blow. Yes or no? Right? Smoke will come from Zener. That is why power rating which you buy should always be greater than the power dissipation. Calculate the maximum power dissipation in the Zener. Calculate the maximum power dissipation in the Zener. Right? Okay, so what is RS? RS equal to Vs minus Vz by Is. Or it is Vs minus Vz is 10. Is is Iz plus IL. Am I right? So see here, this is Is, this is Iz, and this is IL. So what is RS? RS is Vs minus 10 by Is. What is Is? Is is split into Iz plus IL by Kirchhoff's law. Entering current equal to leaving current. Entering current equal to leaving current. Now tell me, in this, how can I get RS minimum? RS minimum. Minimum. Tell me. Suppose I have a X equal to P by Q form. P by Q form. How can I get X minimum? For X minimum, my numerator should be minimum and my denominator should be maximum. Am I right? But if I want X maximum, then my numerator should be maximum and my denominator should be minimum. Yes or no? This is simple logic. If you want minimum, numerator should be minimum, denominator should be maximum, right? So now tell me, what is RS minimum? It is Vs minimum minus 10 by at least how much current should flow? Knee current, Iz knee. Now you tell me, what should be IL for the whole value to be minimum? The whole value to be minimum, IL should be maximum. Maximum. That means for this value of RS, if you are getting knee current, that means for any other value, right? It is going to be always, it is at least more than knee current, it is going to flow. Simple, see here. Just tell me logic, what is the worst case scenario? This RS minimum is called RS, instead of minimum, we have to call it worst case. Worst case RS. This is called worst case, worst case. Now tell me, what is the worst case RS here? Worst case RS. Do you think if a Zener is on for 30 volt, it is on for 20? Or do you think for 20 if it is on, for 21 it will be on, for 22 it will be on, for 30 also it will be on? So Zener, worst case is what? Minimum voltage if I give, 20 volt if I give, and Zener is on, means what? Zener is on for any voltage greater than that. That is simple logic. Now, suppose my load current, I don't know how to explain this. Suppose I have a common emitter amplifier that takes a current of 10 milliampere, 10 milliampere. Like that, 10 milli, 10 milli, 10 milli, 10 milli, 10 milli, 100 milli, 100 milli means I can maximum connect 10 amplifiers in parallel. 10 amplifiers in parallel, 100 milliampere. Now I want all my 10 amplifiers to work. 10 amplifiers to work, or someday I will connect only 5. Someday I will connect, but 10 should work. It is not that 5 it will work, 6 it will work, 10 it will not work. No. For 10 to work properly, it has to draw a current of 100 milliampere. So what I'm saying is, worst case, for 20 volt input, if I'm getting 100 milliampere, see here, for 20 volt input, if I'm getting 100 milli, IL max is 100 milliampere, that means you give any voltage greater, the Zener will never go to off state. Because what happens when I remove the load? Suppose load I remove and put in my pocket, what will happen? Where will that extra current go from source? The extra current will always go through whom? Zener. The extra current will always go through Zener. So if my load is 100 milli, if my load is 100 milli, 10 milli is flowing. If my load is 50 milli, extra current where it will go? Through Zener, more than knee current. If my load is only 20 milli, extra current will now go through Zener. If my load is 0 milli, full current from source is going to go through Zener. So Zener says, boss, if all the devices are on at the load, at least 10 milli if I get for a minimum voltage, then you make any changes in the circuit, I will always get a current more than knee current, right? That mathematics is telling us. Mathematics says that don't break your head. Numerator should be minimum, denominator should be maximum. So it is 10 by 110 milli. How much is 10 by 110 milli? Calculators tell me 10 by 110 milli. How much you will get? 10 by 110 milli. $90.9 ohms. So if I put 90.9 ohms, happily Zener will never go to off state. Will never goes to off state, because you put 90.9 and calculate IS. Calculate IS. This IS will be 100 milliampere plus the Zener knee current, 110 milliampere. So if you put, see how nicely they have designed, right? 110 milliampere will flow from source for RS this value, right? What is PZ max? It is VZ into IZ. How much is VZ? 10 volt. IZ is going to be IS minus IL. IZ is going to be IS minus, because what is IS? It is IZ plus IL, Kirchhoff's law. So IZ is going to be IS minus IL. And what is IS? It is VS minus 10 by RS minus IL. This is PZ max. PZ. This is PZ. Now tell me, what is PZ max? So now tell me mathematics, when this factor is going to become maximum? Maximum. Numerator should be maximum. Denominator should be minimum. Subtraction is there. What will you say? Subtraction. I want this factor to be maximum. So subtraction IL minimum, you have to write. Because I want maximum. So what is PZ max now? it is going to be 10 into maximum minus 10. What is maximum input? 30 minus 10 by 90.9 minus 0. See, so much hasty, right? What is the hastiness here? We are saying that, boss, what rating will you choose for Zener? What rating? Full Zener should burn like anything with heat. When Zener will burn like anything with heat, first step is you remove load. If you remove load, all that current will flow through Zener, right? First step. Second step, will you give minimum voltage or maximum voltage for more heat? Maximum. Give full 30 volt input, remove the load, put in your pocket. Now Zener will burn like anything. All the current will flow through Zener. That is logic. Mathematics also says the same thing. Mathematics says numerator should be maximum, denominator should be minimum. So 30 minus 20 by 90.9. So how much is this? What is the value of this? How much is the value? PZ maximum. Calculator. 2.2. What is the units of power? Watt. The units of power is what? Watt. Am I right? 2.2 watt. That means the power rating of the Zener should always be greater than the power dissipation maximum. So this is the Zener that you are going to buy. So this is the Zener that you will buy. So what sort of Zener that you're going to buy now? 2.2 watt is maximum. Buy 2.5. It will survive. 2.5, 2.6. If you buy from the market 1.2, 0.5 watt, chota 0.25 watt Zener means finished. Zener will go for a toss. Zener will kick the bucket, right? If you want Zener to survive, then your maximum power rating which you are buying will always be greater than the maximum dissipation rating. So when Zener will burn with 2.2 watt, tell me, when Zener is going to burn with so much of power, you have to give full input voltage and remove load. If you remove load, complete current IS and IZ will be same, and the Zener is going to burn with that heat. Are you getting? That is what mathematics says. 30 minus 10 by 90.9 minus IL is 0. Zero current means we have removed the load. All the current will flow through Zener. Okay. Now suppose the shopkeeper says that, sorry, 2.2 watt Zener is not available. 2.2 watt Zener is not available. How to decrease? How to decrease the power dissipation? Power dissipation in Zener. How to decrease the power dissipation in Zener? If such a Zener, 2.2 watt, such a big motor Zener is not available in the market, then how will you decrease the power dissipation in the Zener? Tell me. In this equation, how can I decrease this value, PZ max value? Any suggestion how to decrease this PZ max value? How to decrease the power dissipation maximum? Very good. Increase RS. They are saying increase RS. Okay. But how will you increase RS? How will you increase RS in that RS equation? How you will increase RS? How to increase RS? Yeah. How to increase RS? Your IL should be less. You cannot have 100 milliampere. Yes or no? If you are, very good. How to decrease power dissipation in Zener? So what is the idea now? What is the suggestion we are giving? Suggestion. The suggestion is, if IL max decreases, then if IL max decreases, then RS will increase. If RS will increase. If RS increases, then the power dissipation maximum will decrease. So if IL max decreases, that means Zener should not have a range of, what is the range there? 0 to 100 milli. 0 to 100 milli is this current. See here, this current is 0 to 100 milli. 0 to 100 milli. So for such a range of current, maximum current, what if I make it 10 milli? 0 to 10 milli. What happens if I make it 10 milli? If I make it 10 milli, then IL max will be 10 milli. 10 milli plus 10 milli, 20 milli. Your RS will increase. If RS increases, then the power dissipation is going to decrease. Almost 10 times it is going to decrease. So, good suggestion, right? But how will you decrease IL? That is more important. No? How to decrease IL? How to decrease IL? What is IL, sir? What is IL? What is IL? What is IL? IL is some current which is a subtraction of IS and IZ. Am I right? Some IS will flow, and then it will sink through IZ. Whatever is remaining is going to flow through IL, right? So what I'm trying to say is, this is RS. Here we are having VS. This is Zener. And here, this is IS. This is IZ. And here I'm going to have IL. Am I right? Here I'm going to have it. This IL value, we have to decrease, I'm saying. We have to decrease. So, the load is getting some IL, but that IL we have to decrease. Can I make this current? Can I make this current? Suppose this is my load. This is my load, RL. And here I'm having IL. Here I'm having IL. But when I'm writing Kirchhoff's law, IS equal to IZ plus IL, can I make this IL as divide by beta? Can I make this IL as IL by beta? Then how will you write the equation? When you're writing equation, you'll write like this. You'll write like Vs minimum minus 10 by IZ ni plus IL by beta. You'll write Vs minimum minus 10 by IZ ni plus IL by beta. Then this value is small, RS will increase. So you have to isolate this. We want some current that is flowing here to be small. So how will you make it small? To make it small, what we have to do? To make it small, what we have to do? We will have to connect it like this. We have to connect it like this. So now this becomes the base current, no? This becomes what current? Base current. So in the equation, how you will write now? Here, this fellow, we are going to make him as IB. If you make him as IB, naturally the current is going to, denominator is less. RS will increase. If RS increases here, can you see? Then naturally your PZ is going to increase, right? So this is a good suggestion, right? Of course, this it looks zigzag. Let me draw it a little neat here. This is RS. This is your Vs ripple. This is your Zener. Am I right? Zener, Vz. But don't connect directly a load here. Directly a load RL. Don't connect it. If you directly connect a load RL, then this is a problem. So instead, what we are doing, this one, I'm going to connect a BJT like this. I'm going to connect a BJT like this, such that this current is going to be IB. This is IL. IL. But what is the disadvantage in this circuit? The disadvantage is your V0 is not going to be Vz. There is a drop of how many volts? 0.7. So your V0 is going to be Vz minus 0.7. That is a disadvantage. But otherwise now the Zener size, can you see my hand? The Zener size will shrink now. The Zener will say thank you very much, because while calculating initially, what are you writing? Is equal to Iz plus Ib you will write. First calculation, Iz plus Ib. Ib is naturally small. What is Is? Vs minus Vz. Rs equal to, what is the calculation? Tell me. Rs equal to Vs minus Vz by Is. Is equal to Iz plus Ib you will write. You will not write IL. Who is isolating now? The Zener with the load is being isolated by a transistor. A transistor. Now the supply, the current has to come from here, right? This is a VCC supply here for this. Right? So now the Zener size is less. Zener power dissipation is decreased. Power dissipation is decreased. Power dissipation is decreased, right? Okay. So for this, we will take this as a problem and calculate. Otherwise, you will not understand. Calculate what? All currents and voltages. Beta equal to 50. VB on 0.7. So this is Vs. This is your Vs. Vs you can give some voltage, 18 volt will give. This is 300 ohms. So previously only load was connected. Now we have isolated it with a BJT, right? Okay. So how do we solve this? Here there is 0.7. Am I right? So V naught equal to Vz minus 0.7. 10 minus 0.7, 9.3 volt. Then what is this IE or IL? IE equal to 9.3 by 1K, 9.3 milli. Then what is IB? It is IE by beta plus 1. It is 9.3 milli by 50 plus 1, 50 plus 1, 51. Because I gave beta equal to 50. So all currents are known. Now what is IS? What is IS when this is 18 volt here? IS equal to 18 volt minus 10 by RS. It is 18 minus 10 by RS is what? So in the exam there is no variable. There is no variable. He has given a fixed voltage, 18 volt. 18 volt, RS is 300. It is 300 ohm is IS. Then what is IZ? Give me KCL now. Entering current is leaving. Entering current is leaving. IS equal to IZ plus IB. Therefore, IZ equal to IS minus IB. IS minus IB. What is IS? 18 minus 10. 8 by 300 minus IB. How much is IB? 9.3 by 51. 9.3 by 51. Right? This is milli. 9.3 milli by 51. This is 8 by 300. How much is IZ? What is power dissipation now? Maximum power dissipation. Power dissipation. It is going to be Vz into Iz. So what is this 26.66 Rohit? 26.66 milli is what? Surya 0.182. 26.5. IZ is 26.4. So this is going to be 10 into 26.4. 26.4. That means 260.4. 0.26 watt. So what is the power dissipation there? 26.5 milli into 10. 260. That means 0.264 watt. The power dissipation has drastically reduced, is it not? The power dissipation has drastically reduced. It was around 2.2 watt, if you remember, just by connecting a BJT, a power transistor, because such a big Zener is not available. Instead, what you have to say? You have to go, suppose you went to the shop, shopkeeper says, boss, sorry, 2.2 watt Zener and all, is not available. Chota Zener hai, le lo. Then what you have to say? ठीक है, एक power transistor दे दो. Extra power transistor you have to buy. You have to buy one extra power transistor and go and connect, because such a big Zener is not available. You cannot buy such a big Zener, right? So the power dissipation has drastically reduced to 0.264 watt, right? Okay, that's great. But now the question is it a variable DC source or a fixed DC source? Is it variable DC source or fixed DC source? This is a fixed DC voltage. This is a fixed, your VCC is fixed, no? Your VCC is fixed. Suppose on this circuit, what is your VCC? This is your VCC. This is 9.3 volt, am I right? 9.3. Suppose I want that to be 5 volt. On Monday, 5 volt. On Tuesday, 6 volt. On Wednesday, 7 volt VCC. On each day, I want a different VCC supply for my amplifiers. Then I need a variable DC source. No, it is not. It is fixed DC 9.3, 9.3, 9.3. So current range you have increased. You have increased the current range now. Current range with this transistor, with the transistor. The transistor is also called pass transistor. In some books, it is called pass transistor. Why it is called pass transistor? Because from the supply, the current has to pass through this transistor, right? It is called pass transistor. You have increased the current range with pass transistor. Current range with pass transistor. You have increased, right? But is it a fixed voltage or variable voltage? It is a fixed DC supply. DC supply. It is not a variable DC. 9.3 volt, 9.3 volt, 9.3 volt fixed you will get. Fixed DC supply. And I told you already, this 0.7 is also dependent on temperature. No? In biasing we discussed. 0.7 volts is also dependent on temperature. What happens if temperature increases? There is a change of 2.5 millivolt for every 1 degree rise in temperature. So naturally your output will also change. It is not 10 minus 0.7 fixed, because with temperature 0.7 will also change. So how can we have a circuit that is not dependent on temperature? Your variable, a constant DC voltage, right? What is the disadvantage in this circuit? Is not disadvantage, limitation. Limitation is the output DC voltage is fixed. Is fixed. It cannot be variable. It cannot be variable. Moreover, the output depends on VB drop or temperature. The output is going to depend on VB drop or temperature. Yes or no? Then how you can have a variable DC power supply? How you can have a variable DC power supply? So I am having a ripple voltage. I am having first a ripple voltage. Am I right? I am having a ripple voltage Vs, variable. And this I have given it to Zener. And please carefully observe here. If you directly connect a load, here, what is the problem if you directly connect the load? Then the power dissipation in Zener will increase. If the Zener power dissipation increases, the size of Zener will also increase. Then I told you one suggestion. What is the suggestion? Don't directly give it. Decrease this current by connecting a transistor here. If you connect a transistor here, then naturally the base current will decrease in that calculation, right? Suppose I want this current to be 0, then what can I do? I want this current to be completely zero. Then the Zener size will still become less. Your IB, there is no question of IB here. This current 0. So to make it 0, what I'll do is I'll connect a voltage divider here, RF and R1. And here I want to take my VCC supply. Now you tell me, so this is a very, very popular circuit. Now you tell me, when a positive voltage is given to positive terminal. What is the output? Positive. The diode is on. When the diode is on, there is what feedback? negative feedback, then V plus equal to V minus equal to Vz. V plus equal to V minus equal to Vz. So this is Vz. Am I right? And can op amp draw current? What is the current drawn by an op amp? 0. Right? So here you are having V naught. V naught. Here you are having V naught. So give me a KCL here. KCL. Entering current equal to leaving current. V naught minus Vz by Rf equal to Vz by R1. So your V naught is 1 plus Rf by R1 times of Vz. So this is a non-inverting amplifier. Now see your output, two great advantages. One is there is no 0.7 drama. Your V naught is 1 plus Rf by R1 Vz. But by changing Rf for R1, I can have a different VCC supply, VCC. Now your VCC or V naught, can be changed by RF and R1. So with the ratio RF and suppose RF and R1 both are 1K, then your V naught is going to be 2 times of Vz. Suppose RF is 0, then your V naught will be Vz. So by changing RF and R1, right, or making one variable, you can have a different DC output. You're going to have a different DC output, right? So this one, so a good regulator should have two things now. Two things. One is an error amplifier. And whenever you give negative feedback, what will happen now? Your VOP will change, but your V naught will not change. What is VOP? If you go up, it is V naught plus 0.7. It is going to be V naught plus 0.7. Your VOP will change, but your V naught is not going to change. Are you getting? So there should be an error amplifier. There should be a pass transistor. So how you are able to make it variable? You can make a note here. The voltage range is ensured by error amplifier, and the current range by pass transistor. So what do you mean by current range? If you change load, current will change. If you change the load, so a DC source is there. Now this voltage is fixed. This is a load RL. So if I change load, current will change. If I change load, current will change. Who is deciding this? Is this transistor. See here, suppose if my load changes. Yeah, in this previous problem. See here, if instead of 1K, I make it 2K. What will happen if I make it 2K? If I make it 2K, my current will be 9.3 by 2K. If I make it 100 ohms, 9.3 by 100. If I make it 5 kilo ohm, 9.3 by 5 kilo ohm here. So when this 1K keeps on changing, the current is also changing. Who is doing this? Transistor. But the voltage will always remain constant. But what op amp is doing when you change the load? Where op amp, if you change RF and R1, it is going to give you a different voltage. So this variable is by op amp, right? This current is changing because of the transistor, pass transistor. When current will change? When load changes. You change load, current will change. You change load, current will change. Are you getting? So op amp is going to give you a variable voltage, and the current according to the load can be changed because of the pass transistor. Voltage range is ensured by error amplifier and the current range by pass transistor, right? So this problem, they have given it so many times in GATE, but answer is same. V naught is 1 plus RF by R1. Same thing, I will draw it like this. So many times they have given. Let us take Vs same 18 volt. Calculate what? All currents and voltages. Calculate all currents and voltages, beta equal to 100 or 99. VB on 0.7. Okay. So this is V naught. This voltage is V naught. If you have 10 here, when a positive voltage is given to positive terminal, the output is positive. So if this is 10, this is 10. Let me name some currents. I here, I here. This is IE. IE. What should I call this? IC. I'll call this IZ because the current drawn by op amp is 0. Right? So I've named something. So let us solve it. Now let's apply KCL here. KCL V naught minus 10 by 0.5K equal to 10 by 1K. So your V naught is 1 plus RF by R1. RF by R1 times of 10, which is 15 volt. Your V naught is going to be 15 volt, right? Now what is your V naught? What is this IL here? IL equal to V naught by 100. It is 15 by 100. IL. Then what is this I? This I is nothing but 10 by 1K. I is nothing but 10 by 1K, which is 10 milli. Then what is IE? IE is going to be, how much is IE here? It is split into 2. It is split into 2, which is I plus IL. IE is going to be I plus IL. And what is IC? IC is beta by beta plus 1 times of IE. IC is beta by beta plus 1 times of IE, right? Now, what is PZ? Power dissipation of the BJT. The power dissipation of the BJT is given as VC into IC, which is VC minus VE into IC. Now the collector, where is the collector here? VC, and this is VE. The collector is already at 18 volt. 18 volt. This is Vs minus V naught into IC. It is 18 minus 15 into IC. Is power dissipation of the BJT. What is IS or IZ? IS or IZ is same. So what is IZ? Zener current, the source current here. 18 minus 10 by 300. It is 18 minus 10 by 300. What is power dissipation of Zener? It is Vz into Iz. It is 10 into 18 minus 10 by 300. Okay, so I don't have a calculator with me, so you can tell me what is IE. 15 by 100 plus 10. So it is 15 by 100, 0.15, 0.15, that's 150 milliampere plus 10. Is it 160? What is IE? So whenever there is op-amp with negative feedback, what will happen whenever there is op-amp with negative feedback? It will completely eliminate the problem of drift or temperature, because that VB is blanketed with in the negative feedbacks, right? So whenever there's VB stuck in negative feedback, the op-amp completely eliminates that, because your output is never free, is never a function of VB. So what is this VOP here? Can you tell me what is VOP? VOP minus V0 is 0.7. No? What is VOP? It is V0 plus 0.7. So it is 15 plus 0.7. It is 15.7. So if temperature changes, your VOP will change, but your V0 will never change. Whenever there is op-amp with negative feedback, we have seen it will totally eliminate the drift problem. This is something we have learned in biasing. We have learned in what? Biasing, right? So PZ is going to be 0.266. Okay. What is IC? Somebody let me know IC. What is IC? IC. IE is 11.5. Power dissipation is 34.5 milliwatts. Okay, 34.5. Very good. So if you know the power dissipation in BJT, then every calculation you have got. So finally, we were able to design. So in the design, what are the steps in the design? First, we started off saying that my input is variable and my load is also variable, right? Then we have decided the value of RS, and we found the power dissipation maximum is very large. Then we thought, array 2.2 watt from where, who we will give in the market. Then we went to the calculation. We found that this IS equal to IZ plus IL or some current. If I can make that current as small by putting a transistor, pass transistor, then my power dissipation will decrease. But current range you have increased, right? But the problem is it is not a variable DC source, it is a fixed DC source. To make it variable, we have connected an error amplifier also. So the error amplifier with the pass transistor together, right? We have made a variable DC supply, right? And the good thing about this circuit is here at least base current is there. Here the current is almost zero. If the current is almost zero, then you can tell the shopkeeper, right? Give me whatever Zener you have, right? Some knee current if it flows, that is enough. So kuch bhi jo bhi Zener hai de de, right? Any Zener you can bring and connect it here. Current is handled by transistor and the voltage range is given by the error amplifier. So this is a beautiful design, right? Voltage is taken care by op-amp, current is taken care by transistor, but the Zener will always remain. Zener will always try to only regulate the voltage. Otherwise, in first diagram, everything is done by Zener. Zener has to drive the load. Zener should give a voltage range, right? And Zener should give a current range, right? Zener, of course, it will not give a voltage. Voltage is fixed. Current range, it has to supply any changes in current. So accordingly, we have to buy a big motor Zener. So all this headache was there. But now we have isolated it with op-amp and a pass transistor, right? Okay, 9 o'clock sharp. So we'll stop. Any doubts you can ask?
Hello, sir.
Yes.
Sir, how we are writing ICDC equal to I0 by 2?
ICDC. Where is ICDC here?
Yesterday's class, that current mirror.
ICDC is I naught by 2.
That I'm not getting, sir.
Differential amplifier, you should see DC circuits. No? Whenever you are writing DC current, all voltage sources should be shorted first.
That everything I got, sir, but after finding I naught, why we are doing I naught by 2?
No, have you done this differential amplifier class?
Yes,
I'm having a differential amplifier.
that time onwards I have doubts, sir.
2 diodes are there. Both the diodes experience same potential difference. This is minus 0.7.
Yes, sir.
This is minus 5. What is the current here? I or I naught. This current will
Minus
split into 2 diodes, no?
Yes, sir.
Yes or no?
Yes, sir.
This is ground. This is ground for DC analysis. Signal is ground. 2 diodes are there. This is minus 0.7. Some current is flowing. This will divide into 2 parts. What is there?
Okay, okay, sir. Thank you, sir.
Okay.
Hello, sir.
Yes.
Hello, sir. Hello,
Could you
sir.
please open the previous problem, sir? 36 page, I think so, sir. Sir, how to find that IZ maximum, sir, if they ask?
IZ maximum.
Here,
Power
sir.
dissipation only will give you IZ. Power dissipation. Rating of the device will be there. IZ maximum will not be there.
Means
IZ maximum examiner will give only for calculation purpose.
it is no meaning, sir.
You have to buy. See, you are designing one Zener. Maximum power dissipation you will calculate. Accordingly, you will go and buy one Zener. That's all. What is that you have to do with IZ max? From the power dissipation, you can calculate IZ max.
Means for which IZ it won't be gone, sir.
No. For that particular load current, for that particular load that you are using, you have come to a conclusion for PZ, no?
Yes, sir.
That PZ, more than that value, you have to buy in the market.
Okay, according to the PZ, we need to define
First is load. In the design, first, see, you know how many amplifiers you are going to connect, no? Common emitter, whether your amplifier is driving a robot, whether it is driving a small circuit, you know the requirement of load current.
Yes, sir.
Accordingly, you will calculate PZ max.
Okay.
When you go to the market, you will buy a current rating which is slightly more than that. Now, what will be your IZ max? Your IZ max is going to be your IC minus IL value.
Yes, sir. IS minus IL, right.
That's all.
Okay, sir.
It is always reverse, no? Examiner, if he gives a PZ max, then you will calculate maximum, minimum, you will calculate. But when it is a design perspective, you have to think about your requirement. My requirement is this. My load requirement is this. Accordingly, we have to understand. Yes or no?
Yes, sir. Yes, sir.
Yeah.
And again, in 11th
Hello, sir.
problem, sir. 11th problem, sir. I think so. 16F, sir. Not sure, sir.
This one.
15F, sir.
This one,
No, sir. You have given one DC voltage and diode and other, and again one Zener voltage parallel.
This one. Is this
DC diode and Zener diode, sir.
DC voltage?
No, sir. Both.
Acha, characteristics,
DC, DC, I think so. DC and diode, and also parallel to the Zener diode, sir.
This one.
Not sure.
Is this?
No, sir. This one, sir. Sir, here if DC voltage is 4.3, then both are fine, no, sir. Then which
if
will be
DC
on, sir?
voltage is
Both will be on.
4.3, then output will be 2.7. 4.3 minus 2.7 will be dropped across resistor.
Yes, sir. No, sir. Then both diodes will be on, sir.
No. Diode is on, no.
Sir?
The PN diode is on 2.7. How
No,
this
sir.
fellow will be on?
Zener,
Zener, there is no chance, no.
No, sir. In positive cycle that you said that it will be favorable for only diode, no, sir.
Yes.
Sir?
Yes, you are right.
If it is, I mean, my doubt is if DC voltage is 4.3, then the both parallel loads are, or voltage are 5 volts, no, sir. So which path it will choose? I'm asking, sir.
Where it is, once the diode is on, Zener has no chance, no. Difference will be dropped across resistor. I'll tell you
Yes, sir.
something here. See here, suppose I am having a voltage divider like this. I am giving 10 volt here, 1K, 1K. How much will be the drop of in each resistor here? 5 volt, no? Yes or no?
Yes, sir.
Now I'll put
Yes,
one
sir,
diode. What you will do? This will be 0.7. 9.3 will be dropped here. This 1K is gone. That is dummy.
Yes, sir. Yes, sir. Yes, sir.
Are you getting?
Yes, sir.
Suppose if I put a, if I put another DC voltage 2 volts, this will be 2.7, no? Again 1K is gone.
If it is 4.3, then 5 volts, no, sir, total.
Here it is 4.3.
This DC voltage.
This DC voltage is 0.7 plus 2, 2.7.
Instead of
N
2,
minus
sir.
2.7 will be dropped here across this resistor.
Yes, sir.
Ah.
Here it is, instead of 2 voltage, if it is 4.3, then 5 volts, no, sir, total.
This DC you want to make it 4.3.
That's what I'm.
Okay, you can make, then Zener also will be on. Both are on. But that is not my problem, no? My problem is 2 only.
Yes, sir. I'm just asking then which part, positive cycle, which will be favorable, I'm asking. So
if both devices are same, then the current will divide into 2 parts.
I not by 2, same like diodes.
Yes. But such a kind of a device can you make? The construction of diode is exactly similar to Zener. It's not possible, no?
Yes, sir.
Yeah.
Sir, and again in Vidla's current source, not Vidla, sir. The next one, which I don't think his name. I don't get his name, sir.
Wilson.
You said there is point Wilson, sir. In that source, there is error voltage, no, sir.
0.7 error is there. That is only VC. Operating current means IC, no? IC is already same. Mirror current is same. But VC is not same.
Yes, sir.
IC is already same. Is a very good circuit. Current error there in the basic current mirror was 2%. Here it is beta by 1000, 10,000. Current error is ready. It's an excellent circuit. But still people say they'll not keep quiet. No, some error is there. What is that error? Systematic error 0.7. How to eliminate like that? Are you getting?
Yes.
It is a great circuit.
He said 0.7 means it is large in electrons. He said that's why.
No, but that is not IC. No, 0.7 is voltage, not current. Currents are always same. I copy is almost equal to I reference. Mirror means what? Current. Mirror is only for current, not for voltage. But final circuit with 4 transistors, we have made a mirror action for voltage as well as current. VCs are same.
We have overcome that, sir.
And IC is also same.
Yeah. Yes, sir.
Okay. Sir. Right. Next.
Sir.
Yes.
Sir, I have 14F, sir.
14F.
Yes, sir. Sir, here, if we give greater than 5, it will go to reverse bias, no, sir?
Yeah, it will go to reverse bias and give a breakdown voltage of 5.
Yes, sir. If less than 5, it will be, how it will be off?
For 5, it is on, no? For less than 5, it is off.
Actually, last problem you told us, sir, I think 34F or 32F.
34F.
32 or 34. 32, I think, sir. You gave 20 volts, sir. No, sir, last.
This one.
36.
Yeah.
Here, sir. Here you get 20 to 30 volts, no, sir.
Yes.
Then this side also in a reverse bias only, no, sir.
Yes. Yes.
Okay. If in a Zener diode, if forward bias or reverse bias, the diode will be on only.
Yes. If it is if the current is flowing from anode to cathode, it will give small voltage, 0.7. If it goes from
Okay.
cathode to anode, it will give a large voltage. So during positive cycle, this is the current direction. During negative cycle, this is the current direction. But here, all the voltages are only positive. Only positive.
Okay.
If they are only positive, Zener will either be off or it has to give 10 volts. That's all. No question of negative cycle, because my voltage itself is ranging from where to where? 20 to 30.
Yes, sir. Yes, sir.
Okay.
Yes, sir, in normal diode, if reverse bias, the diode will be off, sir.
Open circuit.
Yes, yes.
Yeah.
But here they will not be open circuit. It will give 10
Yeah,
volts.
it will give big voltage for reverse bias, small voltage for
Small
forward.
voltage for forward
In
bias.
between, again, it is also off.
Okay, okay, sir.
Yeah.
34F.
Yes.
So 34F. $34.
Yeah.
Yes. Here, this one. So here the power is also dependent on IL, and if we are minimizing it, then PM increases power. So why are we decreasing it? I didn't get it.
If IL decreases in this equation, see RS equation here.
Yes, sir. This
IL is in the denominator, no? If IL decreases, your RS will increase.
But sir, in the power, this PZ max equation, IL, if we
The
decrease
PZ max,
IL,
that IL is zero, no? IL is zero. We are just
Independent
removing
of the-
IL and calculating without load. Without load, complete current should flow through Zener, no? That is for maximum power dissipation. This RS minimum is to make Zener work. This PZ is only to know the extreme condition. What is the maximum heat generated in Zener?
so the bias condition worst case, this RS minimum.
This RS minimum tells that even if I give 20 volt and if I switch on all amplifiers, still the Zener should get some current. I'm giving a minimum voltage. See, you should never forget that the current IS that is coming is shared in with two people, no?
Yeah,
IZ
IL
and
IZ.
IL. If for a specific value of RS, if your IL takes all the current, IZ will not have any current, no? Yes or no?
Yes, sir.
So that RS should be so minimum, worst case RS, such that this IS should have a current, large current. That current is split into these two, and then Zener should still get knee current. But Zener should never be off. So what we are doing is, to get that large current, we are giving the minimum 20 volt, that's all. Because if I give 21, current will still be large. If I give 25, current will still be large. If I give 30, current will still be large. It is something like I'm having a minimum salary, but I want to make maximum expenses, all expenses I want to satisfy.
Okay.
20 volt is only I'm having. Okay, with 20 volt is my 20,000 of my salary. I have to cater IZ, I have to cater IL, and this IL maximum is 100 milli. So I have to send money for my kids. I have to save some money. Everything I want to do, even with 20,000. Now you are giving me 25,000. Am I not comfortable? I'm very comfortable. 30,000 if you give, I'm still comfortable. So with 20 volts itself, if you are able to satisfy the load requirement, and still the Zener also gets a knee current of 10 milli, that is the worst case scenario. Are you getting?
Oh, sir.
You are not getting. See, that is why you observe this equation. You are only thinking about 20. You have not substituted 25 in that. You have not substituted 30 in that. Suppose instead of 20, you substitute 30 here. What will happen? Your RS will increase, no? You put that increased value of RS for 30 and you give 25 years, Zener will be off.
Okay.
You will think, Arey, for 30 volt it is on. 30 volt minimum current has come. For 25, no current will be there for Zener. So Zener will work only for 30. But if Zener works for 20, then it will work for 25. Because when voltage increases, current will increase. Zener will still get a current more than knee current.
Okay. Okay.
That is why extreme conditions you have to, if you think only 20, you will not get. You put 30 there. You will get some resistance, no? That resistance you put there, and now you vary to 25 you give for that value. Finish, your Zener will not get knee current.
Okay.
If you give 20 minutes, that means it will work only when Vin is 30. But if your Vin is 20 and Zener is getting some current, see, simple Ohm's law. What Ohm's law says, when voltage increases, current will increase or not? Yes or no?
Yes,
For
sir.
my 20 volt, I am getting some current. 25 volt, my current will be more. For 30 volt, that is why at least knee current should flow. Don't make the Zener off. So A bit is
We are looking if the Zener is on
A bit says
in which
that
minimum
please
voltage.
see that the Zener is on for a worst case scenario, such that
Okay.
Zener will always be on.
Okay.
Are you getting now?
Okay, I got it. Yes, sir, I got it. And so why that BJT circuit we replaced it? It was good. What is op-amp doing to it?
Okay. This one, right?
So why is this circuit bad and we
No, it's
went
not
for-
bad. It's got a limitation that the voltage, DC voltage is fixed. See, my son has so many toys. Some toy works with 5 volts, some toy works with 8 volts, some toy works with 10 volts. What should I do? I need only one regulator. By adjusting the value of resistor, I should get the voltage according to my requirement. Can I tell him play only with 5 volt type? I'm designing one regulator. 5 volt output will come. Dad, what about 9 volt? Means sorry, it will not work. So what I should do? I should buy one extra op amp, connect him in a feedback with a variable resistor. Now I'll ask him, boss, what toy
now
you
we
want?
have the control using that resistors.
In that resistor, I'm getting a new voltage, no VCC. I'll connect that particular toy, 9 volt toy. He'll play for one day. Next day he will say, I want 5 volt toy. Then adjust that R resistor. Today 5 volt is there. Measure with a multimeter. Ask him to play. Are you getting?
Yes, sir, I got it. Thank you so much, sir.
Yeah.
Hello, sir.
Yes.
In yesterday's class, 35, yesterday's class.
35. Yesterday's class, huh?
Yes, sir.
Yesterday's class. Yeah, tell me.
35.
35.
Yes, sir.
Yeah.
Sir, in this ID2 and ID3 series model,
Yes.
sir, first equation, second equation, how you do this?
First
First,
equation.
second. Yes, sir.
ID2 by 4 equal to 1 milliampere by 2. This one.
1 mil, ID2 equal to ID1.
No. ID2 equal to ID1 if their W by L ratios are same. But W by L ratio is different, no? VGS is same. W by L ratio is different. In a current mirror, see current mirror here. Basic current mirror you have to see first.
Before 34.
Yeah, this one is current mirror. Can you see? I reference, I copy. Everything gets cancelled. You are getting this important I wrote. Can you see?
Okay. I
The
reference
current
by
divided by
W.
W by L equal to the current divided by W by L. The current here I reference by W by L1 is ID2 by W by L2.
Oh.
Are you getting?
How would equate first two equation? How would
ID2 equal to ID3 because they are in series. Current is in series means only one current will flow, no? What is the question of W by L now?
in 35 days, sir?
35 page. See the current here ID is 1 milli, no?
Yes, sir.
ID1 by 2 equal to ID2 by 4. ID1 is 1 milli. 1 milli by 2 equal to ID2 by 4.
ID1 and ID2 both are series, no?
ID1 is 1 milli.
ID1 and ID2 both are series, sir.
They are not in series. That is a current mirror. ID1
Oh.
by 1 W by L1 equal to ID2 by W by L2. But ID2 and ID3 are in series.
Okay.
you
Same
getting?
second equation also, sir.
Same thing
Second
we are
also,
writing
sir.
everywhere.
VGS are equating.
For all these transistors, VGS is same. If the VGS is same, then the relationship it is between ID and W by L.
Sir, in 37 F, sir. 37 F. Sir, in this VGS equal to 2 volts.
Here, no W by L is mentioned. ID is same, no? If ID is same,
ID is
VGS
same.
will be same.
VGS.
So VGS, this is X, this is also X. X plus X is 4. X is 2, no?
Okay, sir. For you one is
If this is 2, this is also 2 here. If this is 2, this is also 2 because parallel connection. If this is 2, this is also 2 because same current is flowing.
in today's class, page number 1F. Today's class.
Yeah.
Sir, in this Vx equal to VB1 minus VB1. Sir.
This is VB1, no? This is VB1. This voltage is VB1. Is there
Yes, sir.
VB here? Can you see VB?
VB.
This voltage is VB.
Yes, sir.
This voltage is VB.
Yes, sir.
This voltage is VB.
VB.
This voltage is VB.
Yes, sir.
Then this voltage is VB.
Okay. VB1 minus VB.
This is VB1. This is VB2. VB1 minus VB2.
Sir, in 9F, sir. Page number
9F.
9F. Sir, in this 12th problem, you take KVL, sir.
12th problem.
12th problem.
4th problem.
Third problem.
KVL.
KVL, sir.
Yes.
KVL
0.7
means,
VZ. V0 is 0.7 plus VZ.
V0 plus 0.7 plus, no, sir.
This voltage is 0.7 plus VZ is V0.
Equal to 0.
Yes, KVL. Minus VZ minus 0.7 plus V0 equal to 0.
Okay. Sir, in next page.
Enough here. So many people are waiting, no? Fast.
Sir, if G0 diode is greater than 5 volts means, greater than 5.
If VOC is greater than 5, then Zener is on.
Less than means what is we equated that only voltage.
Yeah. Same voltage will be there. Zener is replaced by open switch.
Okay, sir.
Right.
Hello, good evening, sir.
Yeah.
Sir, could you open 18F, sir?
Yeah.
Oh, sir, sorry, sir, 17F, sir. Sir, I wanted a minor clarification, like for this case which you did, VIN greater than 2.7 volt.
Hmm.
So if we take it as 5 volt, then sir, if we get the case comes up that the diode is also on and the Zener is also on, but this case does not exist because the drop would be through the resistor. Is this correct?
Yes, yes, you're right. See, another example I will give you for better clarity. Suppose if I have one diode here and I have two diodes here and I have three diodes here and I give 5 volt here, you know what will happen?
First will be on and rest 4.3 will be through 1 gate.
So all the other will be off, that's all. It is not that three are on means two will be on, two is on means one will be on. Violation of Kirchhoff's law. Can you say this voltage is 0.7 or 1.4 or 2.1? No. You have to say this is 0.7, that's all. Once
That
it is
means that
0.7,
case never
this will be
arises,
off,
sir.
this will be off. So what you said is absolutely right.
So that case never
4.3 is off
arises,
here.
means like in parallel more will be on.
Yeah. The least voltage is going to get on. Others are you are going to get stopped. The other requirement, whatever is there, two diodes, Zener, they are all going to be off. Simple. You should not violate Kirchhoff's law. Yes or
Yes,
no?
sir. Okay, sir. Got it, sir. Got it. Thank
Yeah.
you, sir.
Yeah. Next.
Hello, sir.
Yeah.
Sir, page number 36, sir. So here, so we are trying to make a DC supply voltage, fixed DC supply voltage.
Yeah.
But sir, we are biasing the BJT from the input only.
From the input always. See, that's a very good doubt you have asked.
Sir, it's a loop only. No, we are trying to make something, but we are using it in our same thing only, BJT only.
Yeah. See, let me give clarity to what you have asked. In a BJT, even if VCC changes, your IC will not change. Why it will
Yes, sir.
not change? IC will change only when the base potential or IB will change.
Yes, sir.
But IB cannot change because Zener is there. So
Oh, yes, sir.
when VCC is changing, when a ripple is changing, your VCE will change, but your IC will not change. IC will
Okay.
change only when IB changes or VB changes, but Zener is fixed. So the transistor for the first time is going to give you a fixed VCC from a variable VCC.
Oh.
From an unregulated input, this is an unregulated input,
Yes, sir.
to a regulated output you are going to get. Are you getting?
Yes, sir. Yes, sir.
But you might say, sir, unregulated, you are giving it as VCC. Yes.
Yes, sir. Yes.
BJT function is that. Even though VCC changes, IC will not change. Even though RC changes, IC will not change. VC will change, but IC will not. IC will change when IB changes.
Yes,
They are
sir.
dependent sources.
Okay, sir.
Are you getting?
Yes, sir.
Yeah.
Sir, in the next question also, yeah, you used op-amp there in place of BJT.
Yes. Op-amp
same-
with BJT we have used. No?
Same case will be applicable.
Yeah. Here also op-amp I'll give variable supply only.
Sir, for saturation voltage we give no plus.
Yes. Op-amp will happily work between plus VSAT and minus VSAT, though it is variable.
Okay, sir. That was the only thing. I was getting confused. Like we are
Yeah.
designing something, but again we are using that only.
Yes. Your doubt is our main aim is to get a DC voltage.
Yes, sir. Sure,
Then
sir.
op-amp also needs DC.
Yes, sir.
When you
that's it.
already have DC, then what is the need? Yes,
Yes,
sir?
sir. I was
Very good.
roaming in the loophole only. What
Yes,
are we
yes.
doing?
Yes. Very good.
Okay, sir. Thank you, sir.
Yeah.
Fine, sir.
Next. Next.
Sir, I think everyone
Everyone left.
Because sir, Venkat sir is unmuting all the students at the same time. That makes a lot of mess, sir.
Sir, I have a small doubt.
Yeah.
Sir, in 23F, it's not a doubt. I was just want to ask something. In 23F, if the Zener diode is ideal condition, then V1 will be 5 and V2 will be 0.
Ideal condition.
Yes, sir.
Ideal condition, both will be off. Because 10 volt you have to give now for both to be on.
Yes, sir.
You have given 8. So you cannot say one is open switch, other one will give 5
Close.
volt.
Okay, okay.
Because in ideal, only 2 conditions. Either you give 5 or you give open.
Okay, okay.
So naturally, diode will become open, no?
Okay, sir. So,
Ah.
got it, got it, got it.
Yeah.
That's the only doubt.
Hello, sir.
Is that over, everyone?
Hello, sir.
Yeah, tell me. Just now you asked, no?
29F.
Yeah.
20. Sir, next page. Graph.
Hmm.
Sir, in this Zener, how will you place regulator?
Yeah, the Zener range is that even if Vs is 13.3, your Vz is 10. Even if your Vs is 31, your Vz is 10. So from Iz knee to Iz max, from 13.3 to 31, if you give, the Zener output is always 10 volt.
Okay, sir.
Okay? Yeah.
Okay.
Sir. Hello.
Yes?
Sir, actually, I am not able to understand in the Zener diode last, why are we putting BJT and op amp there?
See, if you don't put BJT there, if you don't buy a power transistor there, the power dissipation in Zener is 2.2 watt.
Yes, sir.
Such a big Zener is not available in market, no?
Oh, yes, sir.
So we have to buy one power transistor and a small Zener for our requirement. But if you buy the same Chota Zener, then fire will come from Zener because the dissipation is more.
Yes.
So then we have to isolate. So where you have to keep it to decrease the power dissipation. In that equation, we have seen that where IL is there, that IL has to be decreased.
Yes, sir.
So that IL I made IB, no, by putting a Z transistor.
Okay, sir. And then we put op amp there because the current within
The moment you put an op amp, the current is
will be
not
zero.
even IB.
Yes,
It is
sir.
0.
Okay. Yeah, got it.
Yeah.
Okay. To further decrease it, we put an op amp.
We put an with additional benefit is what we are also having a variable output.
Yes, sir.
Are you getting?
Yes, sir.
Yeah.
Yes, sir. Thank you.
Okay, shall we wind up? Anybody else?
Hello, sir.
Okay, that's it. Shall we wind up? Anybody else?
Hello.
Yeah.
Sir, in op-amp, that how we are getting that variable resistor we are putting now.
That is a non-inverting amplifier, no? Any non-inverting amplifier with negative feedback, you'll give 1 plus RF by R1.
Oh, okay.
It is non-inverting amplifier.
Okay, sir.
Okay?
No.
Yeah.
Hello, sir.